Good morning, sir.
Good morning. Are you able to hear me now?
Yes, sir. Yes, sir.
Okay. Yeah.
We'll start at 10 a.m., sir. 10 o'clock, we'll start.
Sure. Yeah, I will do that. Definitely. Can we start now?
Okay, sir.
Yeah, I need to share my slide.
Yeah, sure, sir.
Okay. Are you able to see me? See my slides? No?
No, sir.
You are presenting?
Yeah. No, sir. No.
Yeah, it is starting. I think there is a little delay.
Yeah.
You are presenting to everyone, it says, but not yet. Not yet, right?
Yeah, it's now there, sir. We can see
It's
your
there?
slide. Yeah, we can see your slide.
Okay, so good. So I'm going to start.
So can we just introduce and start?
Sure.
Good morning to all of you. Welcome to the second day of the one-week FDP on instrumental methods of analysis, jointly organized by Bishop Moore College, Mavelikara, St. John's College, Agra, and Guru Angad Dev Teaching Learning Center of the MHRD. There will be two sessions today. The first session will be taken by Professor Chandrabas Narayana, Dean Research and Development, JNCASR, Bangalore. And the second session will be taken by Dr. A. Srikanth, Associate Professor, NIT Trichy. I now kindly invite Professor Bessie Mary Phillip, Assistant Professor, Department of Chemistry, Bishop Moore College, to chair the first session.
Thank you, Dr. It is with great joy that we welcome the first speaker of the technical sessions of this one-week faculty development program, Professor Chandrabas Narayana sir. He is one of the eminent scientists in India and currently serves as Dean of Research and Development, Jawaharlal Nehru Center for Advanced Scientific Research, Bangalore. After receiving his PhD in physics from the Indian Institute of Science, Bangalore, he worked as a postdoctoral fellow in the Material Science and Engineering Department at Cornell University, New York, on metallic hydrogen. He then joined Giant CSR as an assistant professor in 1998. He has been associate professor, dean, fellowship and extension, professor and chairman, chemistry and physics of materials unit. He has been a visiting scientist at Material Science and Engineering Department, Cornell University, New York, and a visiting professor in Paris. He is the recipient of several prestigious awards and honors, namely MRSI Medal, Material Research Society of India, Sir C.V. Raman Young Scientist Award, Professor C.N.R. Rao Oration Award, MRSI ICSC Superconductivity and Material Science Senior Award, Misushima Raman Lectureship, Platinum Jubilee Lecture Award of the Indian Science Congress. He has been a Fellow of National Academy of Sciences, India, Fellow of Indian Academy of Science, and Fellow of Royal Society of Chemistry. He has over 170 research publications and 3 patents in his credit. He is an optical spectroscopist, mainly Raman spectroscopy and brilliant spectroscopy. He has the expertise in high pressure research, where he can apply pressures from ambient to millions of atmospheres on the materials to understand the physical nature as well as dense space of materials. He is also an expert in using synchrotron for X-ray diffraction studies under pressure, temperature, and ambient conditions. He also works in many interdisciplinary areas. He has been using Raman spectroscopy in biology for drug discovery and diagnostic applications. He has also been producing several nanomaterials. He started his career in condensed matter physics, but now he has extended his horizon in the area of chemistry and biology also. Professor Chandrabas Narayan sir is having a very close relationship with Bishamur College, especially with Dr. D. Sarjan, head of the department physics. He has visited our college multiple times in the past and is always ready to support and help our faculty and students in their research work. Please join me in welcoming Professor Chandrabas Narayan sir, Dean, Research and Development, Giant CSR, Bangalore. It is an honor to have you, sir, with us today. We are blessed with your presence and we look forward to your talk. Over to you, sir.
Thank you. Thank you for a very, very wonderful introduction for me. Probably, I hope I deserve so much of appreciation. Thank you. And I would like to thank Bishop Moore College, especially Sajan and Teresa, for inviting me. It is a pleasure always to be associated with Bishop Moore College, Mavelikara. And I am happy that I'm able to talk to you today. I thought that I would be speaking on both the aspects, but then I forgot that I had told that I would only be speaking for 1.5 hours. That was my mistake due to my busy schedule here. So just now I decided that I will allow the introduction and the applications of IR to the second speaker from NIT, Trichy. And I will concentrate mostly on Raman spectroscopy. And my idea would have been to have an interactive session, but unfortunately, due to the online aspect of the this talk, webinar, it is very difficult to have an interactive session. That is exactly how I used to always teach. So people will get chance to ask me questions at the end. And also you can actually write to me to get information from me at this email address. And you can get more information from my many talks I have given, and it is there on the web. So you may be able to actually get more information because many of the talks on this area has been put up on the web. Coming to the vibrational spectroscopy itself, it is a very, very important technique. And I would like to actually start from the basics and then go to there. Well, before even we go to the vibration spectroscopy, what we need is basically knowledge of group theory. So many of us have actually heard about group theory, but I would like to recapitulate what is group theory. Group theory in molecules, when we talk about, we actually talk about symmetries. And symmetry, there are many different types of symmetry which is present in molecules. One of them happens to be identity, which is basically if you don't do anything to the molecule or you rotate it by 360 degrees in any direction, then it is called as identity. So if you realize that every molecule would have an identity because it doesn't change its shape or size when you actually when you rotate the molecules. So this is something which is present in every molecule. And here is an example of a molecule which only has this symmetry. This is something which is very interesting because this molecule, if you do any other transformations, which I will be talking about, it will not be having this identity. So basically, whenever we talk about symmetry is whatever you perform, after you perform, it should not look different. The only way it will look different is by putting a label onto the atoms. If you do not put a label onto the atoms, then they look like as if they are the same after performing these operations. So this is what is the thing in symmetry. Now, there is another symmetry which is called the rotation. And rotation is basically you can rotate it by 120 degrees, 180 degrees, 90 degrees, 72 degrees and 60 degrees. These are very important because many of the molecules generally have these kinds of rotational degrees of freedom. If you look at carbon dioxide, if you rotate it by 180 degrees, you can interchange these oxygens and the carbon remains at the same position. So the atoms are indistinguishable because we cannot distinguish one oxygen from other. So this is called 180-degree rotation or C2. And generally, the N is coming from the fact that you are dividing 360 by 180. So whatever is the value you get is the value you write. But in general, it is not the 180 degrees. We actually talk about pi by 2. So 2 pi divided by pi by 2, and then you actually see that if you rotate it twice, you get the full rotation 360 degrees. So that is how, sorry, this is pi. So 2 pi by pi is 2, and that's how the Cn comes. N is actually 2 pi divided by the, in radians, what is the rotation. So if it is 120, it is pi by 3. So basically, sorry, the 120 is going to be it is going to be giving you 360 divided by 120 is actually giving you 3, and that is what is the C3 rotation. So now you see ammonia molecule, if you rotate by 120 degrees, you will actually interchange all the hydrogens if you rotate along this direction. So there is a directionality to the rotation also. Same way, C4 rotation, if it is a square molecule or square planar or any of those kinds of molecules, you will actually have a C4 rotation possible. Now, C5 rotation generally is associated with a pentagon. So whenever you have a pentagonal arrangement of atoms, then you can have a C5 rotation, which means you rotate by 72 degrees or 360 divided by 72, which is 5. And that is what is actually giving you this rotation. And exactly like that, C6. So it is a hexagonal arrangement of atoms. So these are the symmetries in rotation, which is possible. Now, when you actually go to the next one, which is basically reflection. And in reflection, you can have reflection along any plane. And that plane can be horizontal if you consider the molecular plane is horizontal, and then they are called sigma h in general. And when you have a vertical plane, so if you consider one NH bond included in the plane, which is dividing the angle between the NH angle, then that is called the sigma V. And you can also have a dihedral plane. And dihedral plane is generally associated with if you have a C2 along 2 directions and this plane is bisecting the C2 axis or any rotational axes, then it is called a dihedral plane. So these are the planes. If you reflect the atoms around these planes, they actually occupy diametrically opposite positions. So these atoms, this atom will go here, this atom will go here, and this atom will go here. So this is how this plane becomes a symmetry plane, and you will not be able to distinguish the two positions, I mean two molecules in two different reflections. And the other rotation, other symmetry is called the inversion symmetry, where you actually invert all the molecules. So it's a point around which all atoms are actually taken to the other side. So this is an inversion symmetry, and it is present in any of the BAB type of molecules if it's a linear, or you can have inversion symmetry in octahedra. Octahedral molecules have inversion symmetry where all the atoms can be interchanged around a point. And similarly, you have improper rotations, which is called the SN rotation. Here n is again like what we calculated in the case of Cn, and that is nothing but 360 degrees divided by the angle you have rotated, and that is how you get this n. And here this difference is that you also rotate, and perpendicular to that you reflect. So here is one example that you are having a tetrahedral molecule. So you are rotating along this direction by 90 degrees. And then you are, once you have rotated it, and then you reflect perpendicular to this axis. So you reflect around this and you will get this position. So this is the thing. And this is called the inversion as improper rotation. It can be either reflection followed by a rotation, or rotation followed by a reflection. The order of these two symmetries are not important in the sense they actually result in the same system. So this is basically the symmetry operations which are there, and based on this symmetry operations you are actually able to classify all the molecules into a particular symmetry group. And these symmetry groups are very, very important because all the properties of the molecules in these symmetry groups will remain exactly the same. So that is why we will be able to derive information from many of the molecules. If I understand one molecule in that group, I can understand all the molecules in that group. And that's why this group theory is such an important thing. So generally, before I think I have, I think I have missed some slides. 1 minute, just let me exit it. I think I have missed some slides. One minute. Yeah. So vibration. Yeah. So when we are talking about vibrational spectroscopy, we will actually try to find the symmetry of a molecule, and we must use the character tables. And if you are not yet done the group theory at all, it doesn't matter. If you actually write the various groups, you will actually get what are the character tables associated with it. So this is possible in Google. If you just Google any character table of a group, you can actually get that. So I will not go into how I create the group character table, because that will take me a lot of time to actually develop the whole character table itself. How do I develop it? But once we have a character table, that means if I know the molecule, what are the different types of symmetries which are there in the molecule, and I can actually use that symmetries to create this character table which tells me different vibrational modes associated with it. Now what I am going to do is, if I know the character table, then I can always do the following, that I have to first find out, if I have a molecule, what is the point group of the molecule? That is what I would actually try to find. And I will show you an example so that you can understand how I do it. Then I actually find out the reducible representations for it. That is one thing which I will actually find out. And reducible representations, once I find out, I actually find out from the character table which is the irreducible representations, and then find out how many of these irreducible representations actually are included in the reducible representation. Once I do that, I can actually find out how many of them are translational, how many of them are rotational, and how many of them are vibrational in nature. And once we find out the vibrational mode, then we will find out whether it is an IR mode or a Raman mode. So that is how I'm going to actually find out. Now, this is how I actually find out what is the point group of a molecule. This is a simple flow chart which is basically used. So the first question I will ask is whether my molecule is linear. If the answer is yes, then I only ask the question whether it has an inversion symmetry or not. That means this symmetry exists. If it exists, then it is actually D infinity H. And if it is actually not having this, it is C infinity V. That's how I can find out the group. And if suppose I am not having a linear molecule, then I can ask whether this molecule has more than 2 CNs, which is N is greater than 2. If it has more than 2 Cn greater than 2, then answer is yes. Then I ask the question whether it has an inversion symmetry. If it doesn't have an inversion symmetry, then it is a TD symmetry. That means tetrahedral. If it is having inversion symmetry, then I ask only one question, whether it has a C5 rotation. If it has C5 rotation, then it is IH, icosahedra. And if it is not having C5, then it is octahedra. So I can actually find out if it is a tetrahedral molecule, octahedral molecule, or an icosahedral molecule. These are special groups, and these special groups will actually be very, very special. So if this is how I can identify. If the answer is no to this, then I ask the question whether it has a CN, which is any CN exists. Any one CN. It can be C2, C3, C4, C5, C6, any of those things. If the answer is no, then I ask the question whether it has an inversion symmetry. If it doesn't have an inversion symmetry, then it is C1. That means it has only one type of motion, that is identity alone. There is nothing else. It is a most asymmetric molecule. And if the inversion symmetry doesn't exist, then it is, if inversion symmetry exists, it is actually CI, which is basically having inversion symmetry only. And if it is not having inversion symmetry, but it has a reflection, then it is called CS. And if it doesn't have inversion symmetry or reflection, then it is a molecule which doesn't have any symmetry, and that is what is called C1. And C1 is a molecule which doesn't have any symmetry at all. And CN exists. Then the question we ask is whether the CN is there n CNs, C2s perpendicular to it. If n C2s are, so if you are CN, C3 or C2 or any of those, if you have a CN perpendicular, C2 perpendicular to it, then it actually can be only these 3 groups. The question you ask after that is whether it has a sigma H, that is horizontal plane. If it doesn't have a horizontal plane, if it has an horizontal plane, then it is D and H. If it doesn't have a horizontal plane, you just ask whether it has a dihedral plane. If it has a dihedral plane, it is called 2DND. And if it is not having a dihedral plane, it is only DN. And in case if it is not having a C2 perpendicular to the CN, then you ask the question whether it has a horizontal plane. If it has a horizontal plane, it is CNH. If it doesn't have a horizontal plane, but it has a vertical plane, then it is CNV. And if it doesn't have both this horizontal plane and vertical plane, then it will we should ask whether it has a S2N. Here, what we are finding out is it's an even order rotation. Even order rotation exists. If even order rotation exists, then it is actually S2N. If it doesn't have a even order rotation, then it is simply a CN. So this is how we can actually classify all molecules. As soon as you know, look at the molecule. You don't need to do a group theory at all. Just look at the molecule and find out the symmetries. And you answer these questions, you can actually find out the point group. Now, to take an example, I will take water molecule. It's the simplest one. Water molecule is in this form. That is, basically, it has it is actually a bent molecule, and because it has a bent molecule, two atoms identical, HH, and O is at an angle. Now, when you have a bent molecule, you can easily see that it has a rotational degree of freedom. So it has a C2 rotation, and it has a plane of reflection, which is vertical. Vertical plane of reflection is existing. So now if you go back and ask the question, it's not a linear molecule. And does it have more than Cn? No. So you come here, and then if you ask the question whether it has a Cn greater than Cn, which is existing, then it does have a Cn. And the question we ask is whether Cn has C2 perpendicular to it. It doesn't have. So then we ask whether it has a sigma H. It doesn't have, but it has sigma V. So it is CNV group. Now Cn here, the only major rotation is C2. So it is a C2V rotation. So a C2V group. So that is how water molecule is a C2V group, and that's how we can find out. Now what we need to find out is irreducible representation. And for finding out the irreducible representation, we actually do a displacement of each atom with respect to X, Y, Z coordinates. And I will explain to that. And we will sum up all the vectors of all the atoms in place for reducible representation. So whenever we have a water molecule, we can put on all atoms 3 X, Y, Z coordinates. This is how we put it. We can also write a projection of it. If you look a water molecule from the top, it will look like a straight line, but it is not. It is a projection of this. And you can see only 2 axes because this axis is along your vision. So you cannot see this axis. So we have 2 positions we can actually look at this molecule. This will be useful when we actually draw this molecule. Now, how do I find out the reducible representation? Now, reducible representation is easy to do. First thing is, it has what are the different symmetric groups. As soon as you know C2V, you can go and look at the character table and you will know what are the different symmetries present. So you don't even have to find out. The water molecule, the fact that it has a C2V thing, you will see that it has E identity, which means you don't rotate at all, or you rotate 360 degrees. So either of that doesn't change the molecule at all. And the second one is C2, where we can actually rotate along oxygen axis passing through the oxygen in the plane of the OH. So in that plane, if you rotate it, this hydrogen goes to the other hydrogen. And that is how you can have C2. And then you have a reflection which contains all the atoms in one plane, and another reflection which bisects the angle between HOH. And those are the things. So there is one along XZ and another one along YZ. Now let us look at it. What happens when I do the E operation? That means all these axes do not change at all because I'm not doing anything to the molecule. So each of these axes remain in their identical position. If they remain in the identical position, I can give a number 1. So 1, 1, 1, 1, 1, 1, 1, 1, 1. So that adds up. All of these ones adds up to give me 9. So this is how I will get, for operation E, we get a total irreducible representation as 9. Now, when I do a C2 operation, instead of actually looking at the molecule in a bent form, I can project it because I don't have to look at any other atom. So I look at OH. When I rotate, this hydrogen goes to this hydrogen goes to this hydrogen. Whenever the atom moves from its position, I will ignore that axis. I won't count these axes because hydrogen moves from its position, but oxygen doesn't move. So now what happens is that there is a z-axis which is not moving at all. It remains in the same direction, whereas the x-axis goes to 180 degrees, so it comes here. Y-axis goes to 180 degrees, it comes here. So it changes its position, but z-axis doesn't change its position. So z-axis will I will give 1, and this will be -1, -1. So here is -1 is -2, +1. So it will be total is C2 irreducible representation is -1. Now I do reflection. Now reflection is along XZ plane. All my atoms are along the plane. So when I do a reflection, I do not change the position of H, O, or H. It doesn't change. It remains in the identical position, but the axes get rotated. Only the x-axis gets rotated, whereas y-axis gets rotated. X-axis remains in its position. Z-axis remains in its position. So 1 for Z, 1 for X, -1 for Y. So each atom has the same. So there are 3 -1s and 6 +1s. So you have +6 -3, and that is equal to 3. So that is how we'll get irreducible representation for this as reducible representation for this as 3. Now I do another reflection which is perpendicular to this these two hydrogens. So when I do the reflection, this hydrogen goes here, this hydrogen goes here. So in that sense, I do not count this axis. I do not count this axis. I only count oxygen because oxygen changes its position. So if oxygen is having 3 axes, but this y-axis doesn't change, z-axis doesn't change, only the x-axis reflects 1 from here. So that means I will give -1 for this, +1 for y, +1 for z. So there are 2 +1s and 1 -1. So this will be equal to 1. Now I write the total reducible representations. And when I write total reducible representation, I find that there are 9 for E, C2 I have -1, and sigma Vx I have 3, and sigma Vv I have 1. Now I look at the character table. This is the character table of the C2V. You can see E has A1, A2, B1, B2 are the irreducible representations. And this is the values for each of these irreducible representations. Now what I have to find out is how many of them add up to how many irreducible representations. If I add, do I get 9? So this is what I need to find out. And for that, there is a very interesting formula which is given. So the number of each A1 present in this particular operation is given by the following. So how many A1s are there? I want to find out how many A1s are there. For that, I have to find out the order, 1 by order. Order is the total number of representations here. So 1 + 1 + 1 + 1. So 4 is the order. This is 4 is the order here. And then you have to sum over number of operations in the class. Number of operations in the class is whether there is a prefix to this. If there is no prefix, it is 1. And if there is a prefix, that is the number you have to write here. And the reducible character of the reducible. This is the character of the reducible representation. And then irreducible representation, this one. So this into this plus this is what has to be done for all the sums. So here I have done it for all the 4. Now you see 1 by 4 is your 1 by order. So you have 1 is here 1 because there is no prefix to this. Then 9 is the reducible representation into 1. So this is the first term. The second term is -1 And so this is 1 here into -1 into 1 plus you have 1 here into 3 into 1 plus 1 into 1 into 1. So that is how I have calculated. And if I calculate this, I can do it for A1, A2, A3, and A4. Sorry, B1 and B2. All of them I can do that exactly the same way. Once I do this, this value, what I get is, this value comes to be 3, this value comes to be 1, and this value comes to be 3, and this value comes to be 2. So in my irreducible representation gamma total, I have 3 A1 irreducible representations, 1 A2 irreducible representation, 3 B1 irreducible representation, and 2 B2 irreducible representation. Now, from your knowledge of the number of modes which can exist is 3n minus 6. 3n is the total degrees of freedom, and 3n is 3 atoms. 3 into 3 atoms is 9. Now, if you add up these, it is exactly matching. 3 plus 1, 4 plus 3, 7 plus 2, 9. So this is total number of degrees of freedom. And once you have the total number of degrees of freedom, then it actually means you have translation, you have rotation and vibration associated with it. And you know that for any molecule, there will be 3 rotation, translation. And depending on whether the molecule is linear or non-linear, it will be 2 or 3 rotation, and there will be remaining will be the vibration. So in our case, it is not a linear molecule, so there will be 3 rotations. So now we can see that the translation is all 3 atoms moving in the same direction. All the atoms moving in the same direction. There are 3 different directions: X direction, Y direction, Z direction. So this is the 3 translation, and the 3 rotations is one along the Z direction, one along the Y direction, and another along the X direction. So these are the 3 rotations which are possible. So these are remaining. So that means 6 totally have to be removed to find out how many vibrations are there. So 9 minus 6 is 3. So our total number of vibrations will be 3. Now, to find out the symmetry of the molecules, we can find out which is the irreducible representations representing translation mode. So you can see that the translation will be equal to X in irreducible representation or the character table. There will be 2 more columns which are there. The first column is the one which will be used for finding out which of these are translation. So whenever Cartesian coordinate is given, like Z, X, and Y, they are actually related to the translation. So A1 is Z, B1 is X, and B2 is Y. So out of the 9 total irreducible representation, my translation will be X will be B1, Y will be B2, and A1 will be there. So I have to remove them. So that will be removed from this. Now to find out rotation, I just look at Rx, Ry, and Rz. And here I know that A2 is Rz, B1 is Ry, and B2 is Rx. So then my rotation is B2 for Rx, B1 is for Ry, and A2. So these 3 have to be removed. Now the total number of vibrational modes which are present is 3. And for the water molecule, the 3 vibrational modes which has the irreducible representation is 2A1, because if you have removed 1 A1 from this, it is 2 remaining. A1, A2 only 1 was there, that has been removed, so that doesn't exist. B1 has 3, and you have removed 2 of them, B1 here and B1 here. So that means you have only 2 B1, so 1 B1, and B2 is actually present in both of them. So in that sense, you do not have any B2. So these are the 3 vibrational modes which are present. Now we have to find out which vibrational mode is Raman active and which one is infrared active. So this is how we find out. Now you see that this is the vibrational modes associated with water molecule. This is the symmetric stretching. This is the bending, symmetric bending, and this is the asymmetric stretching. So these are the three vibrational modes associated with it. And now we'll find out which of these modes will be Raman active and which of them will be IR active. To find out if it is an IR active, what we have to find out is whether the dipole moment is associated. So you know that the dipole is associated with this molecule because it is a bent molecule and oxygen is electronegative and hydrogen is electropositive. So there is a dipole associated with it. Now the dipole actually will be along X, Y, and Z direction. So all the modes which have X, Y, and Z are Raman, IR active. Now, how many IR active modes are there? These are the two IR active modes. So that means A1 is IR active. So this is the IR active mode. And also B1 is IR active mode. So that means in water molecule, all three modes are IR active. So that means this molecule has three IR active modes. Now to find out whether it is Raman active, you have to look at the quadratic term. So if the modes have quadratic term, all of those modes, quadratic means it can be square, x square, y square, z square, or x minus y square, x plus y square, those kinds of things, or x, y, y, z, and yx. Those kinds of things are all Raman active. So that means in C2V, all these modes are Raman active. Now we have two A1 and B1, all of them are Raman active. So that means we are having all these three modes Raman active. So from this, we can actually easily find out from group theory which are the modes which are IR active and Raman active. So this is how we actually find from character table, from irreducible representations and the reducible representation which you can create by putting axis on top of it. You can actually find out which are the rotational degrees of freedom, translation degrees of freedom, and vibration degrees of freedom, and find out which are the modes which are active, IR active and Raman active. Now I will come to electromagnetic radiations. And electromagnetic radiations, all of us know, it starts from radio waves, which is actually having tens of meters, tens of kilometers in range. And this is how the kilohertz and megahertz is the radio wave region. In the case of microwave, we actually have gigahertz and also in micron level. And infrared comes around hundreds of microns to 1 micron. That is how the infrared comes. And the visible region is very, very tiny region, which comes from around 700 to 400 region. This is where the visible region comes. After that, it is ultraviolet, then X-rays and gamma rays. So these are the comparison of the atomic scales to mountains. You can see the length scales, which actually works in this wavelength. Now, when we look at it, it has also a relationship to the molecular effect. So you can see whenever we talk about gamma rays, X-rays, vacuum, UV, before UV, we are talking about ionization. X-ray, gamma rays are ionization of a molecule. Whereas when we talk about near UV, we are talking about electronic transitions. Visible and infrared, we are talking about molecular vibrations. Then microwave, we are talking about rotational motion. And radio waves, we are talking about nuclear spin resonance. So from lower frequency to higher frequency, we go from nuclear spin resonance to all the way till ionization in molecular effects. Now, what are the different types of vibration different types of spectroscopy existing? We have vibrational spectroscopy, which is infrared and Raman. And both of these are actually bond vibration frequencies, and it is used to determine functional groups in the system. Then we have mass spectrometry, which is actually fragmenting the molecules and measure the mass. This is a very important technique. It is called spectroscopy, but it doesn't have the necessary condition that it has energy associated with it. But since mass also can be said as energy, that is why it is called a mass spectrometry. And then we have nuclear magnetic resonance, which is basically looking at either hydrogen atoms or any of those atoms which have a unpaired spin, and that is what is used for detecting the environment around a particular atom. And then you have UV visible spectroscopy, which looks at electronic transitions, which gives you bonding patterns and various other aspects. So these are different spectroscopic tools which we use. I have already discussed this while I was talking about it. So this is basically how we come to the number of vibrational modes associated with it. Now, when we talk about vibrational modes, we actually, okay, 1 minute. There is something, yeah. Yes, right. So vibrational modes, you can see that vibrational modes are motion of atoms around a particular center of mass. Now this is HF and HCl. You can see that HF moves more faster compared to the HCl because of the chlorine, which is much heavier. And you can see the energy is related to this vibration, and that is given in centimeter inverse in general. We will be discussing further again. So this is around 4,000 centimeter inverse, whereas this is around 3,000 centimeter inverse. And you can see as the mass increases, the frequency decreases. So there is an inverse relationship to mass also. We will be discussing that. Now there is an easy conversion to energy. Whenever you say have 8,000 centimeter inverse roughly, it is equal to 1 eV. So this is about 500 milli electron volts. And this is around 300 milli electron volts. So you can see that the centimeter inverse is directly related to energy itself. Now, when you have water molecule, we have already discussed, there are 3 different types of vibrations. This is the symmetric bending, asymmetric stretching, and symmetric stretching. And you can see that whenever stretching is there, it is higher frequency compared to the bending. So most of the bending modes will come at lower frequency compared to the stretching modes. Now, when you go to ammonia, one more atom, you have number of frequency increasing, and you can see that is symmetric stretching, asymmetric stretching, symmetric bending, and asymmetric bending. What you have to realize is in bending, you have only change in bond angle, whereas in stretching, you have bond distance is actually changing. So it is always requiring more energy to remove stretch a bond compared to bending a mode. Now, as you increase the frequency, atoms, your number of vibrations increase. But depending on the symmetry of the molecule, the number of vibrations will not increase extensively because of the degeneracy. This is symmetric stretching. These two are asymmetric stretching, and this is symmetric bending, and this is asymmetric bending. So you can see that there is a possibility of degeneracies in these modes, which actually means if you look at from different directions, the vibration will look identical. So hence, there is no, we should have expected according to the 3n minus 6 rule, we should have expected for this 7, 3 into 7 is 21, minus 6 is 15 modes, but we have only 6 modes here. The 6 modes are because these are degenerate. It doesn't look different when you look from X, Y, and Z, and that is the reason why these are actually called degenerate modes, and that's how symmetry is there. So whenever you have a very symmetric molecule, the number of vibrations will be less, and when you have an asymmetric molecule, the number of vibrations is more. So it is very easy to distinguish, if you look at the vibration spectroscopy, whether the molecule is symmetric or asymmetric, and that's very quick way to find out the structure of the molecule itself. So these are vibrations are actually fingerprint of the molecule. So the whole molecular vibrations and bending vibrations are always quantized. No two molecules will give you the same IR spectra or Raman spectra. It doesn't give you this thing, except if they are enantiomer. Enantiomer means if it is geometric isomers. If they are geometric isomers, that means the molecular formula is the same, but they are different optically. Optically they are different, but the molecule is exactly the same, but except for the isomerism, which is called geometric isomerism. Only then the frequencies will remain the same. Otherwise, no two molecules will have exactly the same spectra. Then stretching modes generally appear around 1600 to 3500 centimeter inverse, whereas complex vibrations always exist below 1500 centimeter inverse, 600 to 1400, and they are always called as fingerprint regions. Now, just for a quick tutorial on vibrational modes, you can see that when you talk about a simple harmonic oscillator, we actually have a parabolic potential. This is the parabolic potential, and when you do the quantum study, you will get energy states which are equally spaced. E is equal to n h nu. That is how it will come, and that is what you would actually have in this any quantum system. Now, what is the important thing you should realize is that harmonic oscillator model works very well for low energy. But as the atom starts vibrating very fast, it starts producing two things. One is atomic repulsion and attraction, because of which you need to bring in anharmonicity. There are two things which happen. Because of the Coulomb repulsion, this potential doesn't remain as parabola. It actually starts changing in parabola. And also, when it becomes very, very high energy, the atom starts dissociating. And that's why you will have an anharmonicity in this. And this is very important because the energy states, as you go higher, it starts crowding. And that is why you can also have transitions, which usually in harmonic approximation, we can have only transition plus or minus 1. Whereas in anharmonic systems, we can have plus minus 2, plus minus 3, which are called the overtone. That means second harmonic and third harmonic is possible. This is possible only in the case of atoms because of this anharmonicity. Now, when we look at it, you can see here, anharmonic situation, the frequency is inversely proportional to mass, reduced mass, and it is also related to the spring constant. Spring constant is directly proportional to the frequency. So the bond is stiffer, the frequency is higher. Bond is weaker, it is going to have a lower frequency. So this is how we can actually find out bond strength or bond stiffness from these frequencies. So you can see, if you look at HF to HBr, HI, you see as the electronegativity increases, the bonds are actually weaker. The bonds are weaker because it gets more and more ionic from covalent. Now you can see the frequency also shows the same, that it is highest for HF, whereas it is lowest for HI. And you can see the bond stiffness is also reducing. And this is very easy to find out from the frequency directly from using this, this equation. We can easily find out. Similarly, for chlorine and bromine, if you compare, chlorine is much more higher frequency compared to the bromine, because the mass is bigger, and also the bromine-bromine interactions are much weaker. So you can see the bond stiffness also actually changes. Now you can see C double bond O, that is carbon monoxide, and nitrous oxide, which is N triple bond O. So triple bond is much more stiffer, even though we consider triple bond is supposed to be stiffer, but here it is not a triple bond. It is double bond with a covalent coordinate bond. So this covalent coordinate bond makes it weaker compared to the double bond of CO. So here you can see the stiffness of CO bond is much higher compared to the nitrous oxide because of this coordinate covalent bond. Because coordinate covalent bond is only one of them sharing it. So that is actually going to extend the double bond here. So you can see nitrogen also has a triple bond here, and because nitrogen has a triple bond, you see NO and N triple bond. This is a double bond with a covalent bond, coordinate covalent bond, whereas here is a triple bond which is much more stronger because of the nitrogen-nitrogen interactions. And that is the reason why you can see that this is much more stiffer compared to this. So from the vibration spectroscopy, we can actually know what is the bond stiffness of the system. Now I come to the Raman spectroscopy in the system. So basically, now what I am going to quickly go over the Raman is that we are actually looking at light scattering. So that is why I would actually say that whenever light interacts with matter, there are multiple things which happen. transmission, reflection, absorption, and luminescence. All of these things are the major things which happen in the light. But you and me see everything because of the elastic scattering. Elastic scattering means there is no change in the light. The difference between reflection and elastic scattering is that reflection has Snell's law to follow, whereas elastic scattering doesn't have to follow Snell's law. It actually happens in all directions. And that's what is called elastic scattering. Now, along with that, there is something called the inelastic scattering, and that means the light can be blue shifted or red shifted, and that is what is the Raman scattering. So basically, we are looking at this shifted frequency, and this shifted frequency is equal to the energy of the vibration. And when we look at it can also be Raman, it can be also not only because of the vibration, it can be because of the rotation as well as electronic Raman. But today we will be only concentrating on vibrational Raman. So we can actually see that this shifted frequency happens very easily. It can be demonstrated. Here is a blue laser light, and it is passing through this transparent liquid. And this liquid is cyclohexane. Now, what happens is that when light passes through it, because you know that laser will not get bent, so it is impossible for us to see the laser in the 90 degrees. So here is the elastic scattering from the dust particle in the room, and here is the elastic scattering coming from the liquid inside. Now, why it is white? It is because your intensity of the light is so large that your detector is saturated. So whenever the detector is saturated, it gives you a white color. So it doesn't give you blue color, but it is, if you look at it with your eyes, it will look like very bright blue color. Now what you have to do is, to find out shifted frequency, you just put a filter. If I put a filter which only filters the blue light, then I will be able to see if any other light is coming. And you can see the filter that filters the blue light. You can see the blue light is missing here. There is no blue light here. You can see from the liquid, you are getting a shifted frequency, and this is the Raman scattering. So this Raman scattering is directly related to the vibrations of the molecule. To compare between IR, Raman, and fluorescence, you can see that it is using the same energy levels. So you have a S0, which is a ground state coupled with vibration, and S1, which is electronic excited state coupled with vibration. Raman is actually transition between excited state to ground state, and only the difference between the vibrational states. So this gives me very sharp peaks, and it is an inelastic process because it is not directly absorption. Whereas in fluorescence, you are actually going to the excited state, coming down to ground state. So you actually span the complete energy states. So you get a broad band. And if you zoom up, you will see Raman scattering sitting on top of it. You will always have a Raman scattering sitting on the vibration, but since the intensity of Raman is very weak compared to the fluorescence, you will not see these until unless you zoom up and actually look at very carefully. Whereas absorption, infrared absorption, is direct absorption. So you only supply the energy equivalent to the vibrational frequency, and these energies are absorbed and they are removed from the transmission. And that removed transmission gives you which energies are absorbed, and that gives me idea about vibration spectroscopy. So this is the vibration spectroscopy relationship. Now, how does Raman happen? Basically, very quickly, we consider Raman, this is the vibration, any molecule, diatomic molecule I have taken. You have two atoms and the bond. Bond I have replaced with a spring to compare it with the two-ball spring system. And now what happens is, in a classical system, when light falls on it, nothing happens. But in an atom, because atoms and molecules are having charges, because the light is an electromagnetic radiation, it actually has an electric field. So there will be an interaction. So generally, the electric field associated with the light is given by E into, you can give a cos or a sine term, which has two terms in time dependence and the space dependence. Since the light is so fast that the molecule doesn't move, we can actually ignore the space part. We'll only keep the time part of it. So the electric field is varying in time, not in space, because the molecule doesn't move while the light is interacting. So we will not consider this. Now, as soon as the electric field falls on it, you will have the electrons which will respond immediately. It will move away. Usually, the electrons are, this molecule is a neutral molecule. The moment an electric field falls on it, the electrons will shift, but because the nucleus is very, very heavy, nucleus will not move much. So the electron will move in the direction opposite to the electric field direction. And that means you will create instantaneously an induced dipole. And this dipole now will oscillate. This dipole will oscillate because the electric field is oscillating. So you create an induced polarization in the molecule, and that is dependent on the polarizability. And this polarizability depends on the electron's polarizability. And this is very, very important because the electron's polarizability will determine whether this induced polarization will be strong or weak. And hence, it is directly proportional to the electric field itself. Now, if I substitute back, now I know that this induced dipole is oscillating with the same frequency as the frequency of the light which fell. This is called elastic scattering. This is the elastic scattering happening, and it will happen because you know that any dipole which oscillates produces electromagnetic radiation, and that electromagnetic radiation goes in all directions. And this is the elastic scattering. This is if alpha is an quantity which is supposed to be a constant. But alpha is the polarizability of the electron. And when the molecule vibrates, the molecule is vibrating, so the electron has to follow it because the charge neutrality has to be formed. So then the polarizability of the electron will be dependent on the vibration itself. So that means alpha is a function of the vibration, and vibration is nothing but a movement of the atoms. So it is having a coordinate, vibrational coordinate. And so alpha is a function of the vibration coordinate. You know that vibration is an oscillating function. So it is having a frequency associated with the molecular frequency. And this is what is the quantity. Now the alpha, because it is a small vibration, you can expand it as a Taylor series. So it is alpha naught plus dou alpha by dou q at equilibrium times q plus dou 2 alpha by dou q square times q square plus like that, higher terms. Now this is how it is. I have reduced the higher terms. If I include the higher terms, this is the first harmonic, second harmonic, third harmonic. So that is the overtones which will be coming. I am not considering the overtones for this discussion. I will only consider this one. And now what I do is I plug back all the quantities back. Now my induced dipole is actually induced polarization is a function of the frequency of the light and frequency of the vibration too. Now, you know that from trigonometry, this is cos A into cos B is cos A plus B and cos A minus B. So suddenly, now my frequency is associated with frequency of the light. This is the elastic part. And this is the Raman part, which is shifted frequency. Omega L minus omega M is the Stokes-Raman, and omega L plus omega M is the anti-Stokes-Raman. So basically, these two are new components which are created because of the vibration of the molecule. And this vibration is so unique that every new vibration will produce two more such quantities, and that is how you create. Now, what is the selection rule? If dou alpha by dou q at equilibrium is 0, then this is Raman inactive. And if dou alpha by dou q is not 0, then it is Raman active. So this is how the selection rule works. Now, it's very easy to understand this in a diatomic molecule of homonuclear, or you have AB type or AA type. The vibrations actually, when it happens, your polarizability actually is, when you bring the atoms closer, then you are actually having less polarizability. And when the atoms are extended, because the electrons are spread over a long direction, it can be polarized much more easily. So the polarization increases. So decrease polarization to increase. So if I take a slope here at dou alpha by dou q, then it is non-zero. So it is Raman active. Same way, you can see in the this case also it is Raman active. Now, if I consider a triatomic molecule, which is A, B, A, then it is going to be that this is like carbon dioxide. So when I stretch the molecule, the polarizability is higher. And when I compress the molecule, the polarizability is lower. So in a stretching mode, it will be having non-zero slope. Whereas when I do a compression in one direction and expansion in another direction, my polarizability is actually like a parabola. And if I take a slope here, it is zero. So that means this is Raman inactive. And if I do a bending mode, again, when the bending mode is done, you always have polarizability actually maximum when they are bent more, whereas when they are straight, the polarizability is lesser, because polarizability depends on how the electronic densities are there. So the polarizability is actually going up when you go to the bent position, and hence if you take a dou alpha by dou q, it is actually zero. So this is Raman inactive. So in a molecule which is bent, like water molecule, you can see all of these conditions. The water molecule has all the three non-zero dou alpha by dou q. That is why all the three modes are Raman active. So it is very easy to know. But till now, I have never talked about quantum mechanics. I only talked about electrodynamics, very simple classical electrodynamics, and explained the Raman theory. But here is where the problem comes, that why do we have different intensities for Stokes and anti-Stokes? So if you look at this classical explanation, dou alpha by dou q is always same, irrespective of whether it is Stokes or anti-Stokes. But in general, that is not the case. It depends on the what is your energy states. Because as you know, in a quantum mechanical system, as you go to higher and higher energy, the population is lesser. And hence, these intensities are not directly related. So you can actually see that the population will be different. The intensity is directly different. And that is how you can calculate the intensity ratio. For this reason, we bring in quantum mechanics. We don't have to do anything. The dou alpha by dou q, whatever I talked about in quantum mechanics, is given by this. And you can see that there are three Hamiltonians. So it is actually a perturbation theory we have used. So there are three Hamiltonians here. And it is this is the Raman scattering cross-section. If this happens to be non-zero, then it is Raman active. If it happens to be zero, then it is Raman inactive. This is what it is. Now, what does it mean? So when light falls on the atom, electrons actually absorb the light and go to an excited state. Since we are actually not having exactly matching energy states, so how does the electron go to the virtual states? It is very interesting to understand that whenever you excite a molecule, when you have not excited a molecule, then what happens is that you have E1, E2, E3, S1, S2, S3, like that, those energy states. These are the real eigenstates of the function. But the moment you excite, you also create linear combinations of them. And that is instantaneously produced. And those energy states are available. So there are linear combinations of eigenstates, which are called the virtual states. The reason why they are called virtual state is because they cannot remain in that state for a longer time. It is instantaneously coming down. So when it goes up and comes down, it produces electromagnetic radiations, and that is called the elastic scattering. But while it is excited, electrons are having a strong interaction with the vibration. So it can actually transfer energy. So it can create an excited vibrational state, losing energy. When it comes down, it's redshifted. And that is called the Stokes Raman. The reverse is also possible, that the excited state comes down and of the vibration, giving energy to the electron. And now when it comes down, it is anti-Stokes Raman. Now you know that the population of the excited state is less compared to the ground state. So this process will be more compared to this process. Hence, Stokes Raman is always stronger compared to the anti-Stokes Raman. And basically, the ratio of this intensity is directly related to the population. Hence, it is related to KBT. And hence, we can find out the temperature of the sample directly. Now, another interesting aspect of this is the denominator. The denominator is actually excited. There is a laser excitation times the energy state which it goes, and laser scattered light related to the energy states. If they happen to be real states, then the electron can remain for a longer time in this place, and hence this will be a quantity which can go to zero, and hence you will create a state which will have denominator zero, and that can actually create a high intensity, and this is called the resonant Raman. So whenever you have an energy state which is real and you are actually tuning to the laser to that, you can create energy states. It can also happen in the scattered geometry, very rarely, but most of the times we tune our laser to an energy state here. That's the resonant Raman. So whenever we collect a Raman spectra, it is actually related to vibration directly. So it is a carbon tetrachloride spectra. It is a tetrahedral molecule, and you can see that all of these molecules actually have vibrations in this region. Okay. So now when we look at this, you can see that you have stretching, asymmetric stretching, symmetric stretching, asymmetric bending, and symmetric bending. This is actually only bond angle changes, bond distance changes in this thing. So you can see that in the Raman, you see all of these things. And today you have computer programs which can actually calculate all the Raman vibrations or IR vibrations, and you can see what kind of atom motions are there. You can exactly know what frequency is coming. There is Gaussian, there are many calculations, MD simulations, many other things, which actually can calculate all of these vibrational modes. Today, you don't have to really do difficulty. So most of the times, what people are doing is first we do the calculations, find out the vibration modes, compare the vibration modes with what you have got, and then you relate those frequencies, and then you can get it. So this is how you solve the structures. Now, very interestingly, if you look at this frequency, it was not a single value. And you can see there are some wiggles here. It should have been a single value, but it is having difference. Now, very importantly, you can see that whenever you have a frequency very close to each other, one of the ways to actually see whether there are multiple frequencies is to reduce the temperature. When you reduce the temperature, your width of the peak reduces, so you can see fine structure. And this is how the fine structure is there. And suddenly you see there are not one peak, 1, 2, 3, 4, and 5. 5 peaks are there. And that is what is due to, because there are 4 chlorine atoms, and chlorine has a relative abundance of Cl35 and Cl37, 3:1, where the difference in the mass is there. Now, when you actually look at it, these frequencies are associated inversely proportional to the mass, right? Reduced mass. So if all of them are Cl35, then it is 461. And when it is 3 Cl35 and 1 Cl37, it is 468. Now you can see that if it is 2, it is 475. Now you can guess what these two are. It is 3 Cl37s, 4 Cl37s. So that means we have 5 combinations possible, and that is why we get. And also, you know why the intensities are different. Because as you go, this is the most abundant condition, 3:1. So that is the strongest. We can always have all 4 Cl35s, but very, very difficult to have all 4 Cl37s. So that is the reason the intensities are directly. So that means isotopes are having a very big advantage in these systems. Now, one of the biggest challenges is that Raman spectroscopy is a very, very useful technique because it is a fingerprinting technique. You can easily find out what is the molecular structure, because if I have the same group, then I know that the Raman spectra will be looking similar. It is highly sensitive to symmetric bonds, which I showed you, and it is highly sensitive to the bond angle and bond strength. So we can actually find out the geometric conformation of the structure, stresses in the molecules, and sensitivity of the molecule. Raman scattering also can be done with various different frequencies. We don't need to be worried about which frequency we use. We can do with every frequency, and we can do from deep UV to near IR. We can do all of these frequencies Raman. So that is very, very useful. And enhancement of the Raman modes, which is there. That means you can get resonant Raman effects, and we can get a lot of information about electronic state and Raman vibrational frequencies. We can get a lot of information. And then you also have no need of preparation of the sample. You can do it as is condition. So that is a very, very important condition. Now, coming to this problems in Raman, very, very importantly, you can see that it's a very weak phenomena, because if I put around 1 million photons, only 1 photon will be Raman scattered. So that means we have very, very weak signal coming out. The only reason why we can do in most of the samples is because our concentration is very high, because the molar concentration is very high, we get larger signal from the Raman, and hence we can actually do it. Resonant Raman is not possible in every condition, whereas absorption is a much better condition. So IR actually is much easier to do, because absorption is 1 photon goes in, 1 photon gets absorbed. So it's always a stronger process. So that is why most often you'll find vibrational spectroscopy done by IR. But there is a very important thing you should remember, that Raman scattering and IR scattering has a very distinct feature, something called mutual exclusive principle. If my molecule is highly symmetric, if it has a centrosymmetry, then all the Raman active modes will be also IR active. If it is having centrosymmetry, then IR active modes are not Raman active, and Raman active modes are not IR active. You can see this frequency is not matching with this. This frequency is not having any matching. This frequency is not matching with this. It is slightly shifted. There are frequencies here which are not matching here. So you can see there are frequencies which do not match. So whenever the molecule is symmetric, the benzene rings are symmetric, then you do not have IR modes, Raman active, Raman modes, IR active. But the moment you remove the symmetry, you see that all the modes are actually Raman active or IR active. It can be Raman active and IR active. So basically, you can see this is one of the problems, that if your symmetry is there, center of inversion is there, then you will have mutual exclusive principle followed. Now, I'll quickly go through some applications, how Raman is very effective in finding out the sample, because it is easy to do. It is also for IR true, but Raman is much more effective because you don't need to prepare the sample. In short 5 minutes, I will tell you some of the applications. You see that when I go from CH3OH to C2H5OH, these two molecules only have a difference in CH, whereas all of the others are same. And you can see the spectra is very, very different. So by just looking at the spectra, we can immediately know whether it is what kind of molecule it is. Even a change of CH2 creates a new modes, and that is why it is like a fingerprint. You can see the COH stretching is present in both of them, because the OH is independent of this molecular structure. So that is why the OH stretching remains the same, but even the CH3, CH2 region is stretching is actually varied, and you can see it. Now, another important thing is, today we have been always talking about, in the news, you would have heard about this molecule, MDMA. Today, when you talk about Sushant Singh's death, you are talking about MDMA, drug use. Everybody has talked about this. Nobody knew what it was till now. But actually, this is a drug which is called ecstasy. And ecstasy is actually used by people for getting high. Now, to find out if it is a ecstasy molecule or its primary component, this is the starting compound and this is the final compound. You see the difference is there is a benzene ring here, which is broken here because it is actually no longer a benzene. So now you know that the breathing mode, that means all the 6 carbon atoms going out and in, will not happen in this case. So this frequency will be disappeared. You see, this is the frequency associated with this breathing mode. So you can see this frequency is missing in the parent compound. You can see most of the other things are similar, but this is missing. So just by doing a Raman, you can easily find out whether this is the starting compound or this is the this is your drug, which you are actually trying to find out. Even in a trace detection, it is possible. So that is so beautiful in systems to distinguish between starting compound and ending compound. So this is a very useful technique to do. Now here is the SO4, and as I showed you in CCl4, it also has a symmetric, asymmetric stretching, symmetric stretching, asymmetric bending, and symmetric bending. You can see that these are exactly the same. Only the difference is the frequency is different for SO4. SO4 is also a tetrahedral molecule. Now, the only difference between the green spectra and the red spectra is one has sodium, another one has magnesium. And you can see the stretching mode. I'm just zooming up the stretching mode. The stretching mode has shifted. Now, why did it shift? Because of the presence of magnesium. Now, you know that magnesium has a charge 2+, whereas sodium has a charge 1+. And now, the moment you have a Coulomb interaction, you know the force applied by sodium is much less compared to the magnesium. And that is why the force is dampening this vibrational mode. And that is why the frequency is shifted to the left. And that means it is becoming weaker. So that means the SO4 is not able to execute this much more easily. It is much more weaker in the sense SO4s are actually weaker. Now here is a molecule which is very interesting, because this is a molecule coming from a plant extract, and this is another molecule which is exactly same. If you look at the molecule, if you are not an organic chemist, you will immediately say that they both are identical. The only difference is that there are two chiral centers here. That means these two centers are geometric isomers. So that is very important, because if you look at it, I said that when you have a geometric isomer, no frequencies will shift. There won't be any change in the spectra. So if you look at the spectra, I told you the benzene ring will be having a breathing mode. You can see the breathing mode here, 1000 centimeters. Both of them have breathing mode. Now, you look at very carefully this region. If you look at this region, you see the intensity ratio is different. If you look at this region, the intensity ratio is different. So you see some intensity changes, but not the frequency change. This intensity change is because of the chiral centers, and this is the reason why you can identify whether this is pseudo-ediphin or ediphin. Why is it so important? Because this is a molecule which doesn't work for asthma, whereas this works for asthma. So this molecule is more important compared to this. And that is why we want more of this compound. And if you want to distinguish in your molecule without doing any complicated system, how much of this is there and how much of this is there, you can actually quantify by just looking at the Raman. Another interesting aspect of Raman is that you can actually also find out stresses in the molecule. Here, I have taken an example. You all know diamond. This is a diamond. And in the diamond, because while it is forming inside the sand, you can always have inclusions. This is calcium silicate. You know, silicate is present in the sand. So deep earth, you have many minerals which are present. This is one of the minerals which is present, and it is embedded inside the diamond. Now, diamond is very beautiful because it can be found out very easily from Raman, because it has a sp3 hybridization, and this sp3 hybridization gives you a 1332 peak. If you have a 1332 peak, you can be rest assured it is a diamond. No other molecule will give you 1332 peak very easily. It is a very sharp, very intense, and no other peak will be existing in the diamond, only the 1332. So if I actually map this with 1332, I see that as you go closer to this laranite, you start finding that the 1332 peak becomes 1338. Now, why should it shift when it comes here, whereas it is 1332 here? All black is 1332, whereas yellow is 1338. Now, what is the reason why it happens? Now, when you actually 1332 to 1338 is because if your spring constant is increased, that means you are compressing the system. When you compress the system, you can actually increase the spring constant. That means you are bringing the atoms closer. How do you bring the color? You can do a pressure study. So you can see that if you apply pressure on diamond, it can shift from 1332 to 1338. And what is the pressure required? it is about 2.7 gigapascal, which is equal to 27,000 atmospheres. So you can see the pressure on the diamond here is around 27,000 atmospheres. So you can see an inclusion of a very, calcium silicate is much weaker compared to the diamond, but just because it is included here, it creates stresses. And the moment it creates stresses, the moleculars or the material properties would change. And this is now you can understand why when you dope a molecule with a different size atom, you actually create a new electronic structure because you create stress. And because of the stress, you change the band structure of the molecule or the solid, and that creates electronic transitions. And that is how stresses actually are possible. So you can find out from the Raman easily what the stresses are there. This is useful when you are growing a thin film. You want to know stress in your thin film, you can actually do the Raman and get the stress in the thin film, whether it is tensile stress or compressive stress. Another interesting thing is Raman can determine whether it is a amorphous material or it is a crystalline material. Whenever it is crystalline, it will be sharp. Amorphous, it will be broad. Another usefulness of vibration spectroscopy or Raman in principle is if I have two different molecules, I can find out the concentration of one molecule inside the other. So here I have dissolved in nitrophenol, this is the nitrophenol, in dichloromethane. Dichloromethane is a universal solvent, and you can actually dissolve this nitrophenol. And if I change the concentration, I actually see the nitrophenol peak actually goes down. And that means I can find out the concentration. So this is how I can actually plot it. And at any intensity, I can find out what is the concentration of the material. So since I have exhausted my time, it is already 11:25. I would like to have questions. I will not go into the instrumentation part of it. I will actually stop at this. Teresa, I am actually stopping here for questions, and so that the next speaker can start after this. Yeah.
Sure, sir. Sure.
Yeah.
Professor Bessie?
Yes, Miss. Participants, please post your doubts and questions in the chat box. Thank you very much, sir, for your wonderful presentation.
Thank you. It would have been better if it was interactive, but I am sorry, we have to do it in a monologue way. So if people can ask questions, then it is fine. Otherwise, if they are finding it difficult to write the questions now, they can write it to you and you can pass on the questions to me, and I will reply to those questions and write the answers for you so that they can be given to those people also at a later stage. No problem.
Sure, sir. Sure, sir.
Yeah, somebody has asked a question. Stress in thin film. Can you read that question? There is a chat.
Yes, sir. Shall I read it out?
Yeah.
Would you expect difference in stress on thin films based on their thickness?
Yes, of course. Absolutely correct. See, when you are growing on a substrate, when you, I hope you can see me when I'm talking. I will actually stop the presentation so that it is easy for you to see me. And then let me stop. Okay, I've stopped the presentation. Now you can see me, I hope.
Yes, sir.
You can see me. Okay. So what I'm saying is that if you have a thin film, you have to grow thin film on a substrate. And you know that no substrate is exactly matching exactly the lattice parameters with the growing substrate. So when it is growing, there will be some sort of a variation in the bond distances in the system. As the thickness keeps on increasing, what happens is that slowly the stress will be reduced and then it will become good crystal. So to a distance of about few microns, always there will be too much of stress in the thin film. Now, if you do the Raman, you can easily see that stress difference. When it is very, very thin, the stress will be very high. And when it is thicker and thicker, the stress gets released because of thickness of the sample. So generally what happens is that if you are growing a thin film and if you want good thin films, generally people will try to grow a little more thicker. But there is an issue here, because many a times the structure is very, very important in the properties. And if you are using a thin film for a device, most of the characteristics will come from the interface. And that is why the interface stress has to be reduced as much as possible for the thin film to be useful. So that is why if you do a Raman, you will immediately know how much of stress is there, whether your substrate is working very well or you are able to do it correctly or not. So the device failures will happen or not. All these things can be found out without destroying the substrate and the thin film.
Sir, and the question from Shija Mall. In IR spectral interpretation, fingerprint region did not explain. Why?
No. I didn't teach IR, but what I'm talking about is that in IR, most of the times fingerprint is a complicated region, because the complication in the fingerprint region. So when you look at an IR spectra, there is a very hypothetical line which is called the 1500 centimeter line. Any frequency above 1500 centimeter is related to the functional groups. So you always use this functional group to find out what is the molecule structure. Organic chemistry, if you are actually working with organic molecules, you always look at the functional group, and immediately after looking at the functional group, you can actually say that what are the different types of bonds present in this thing, and you can try to guess what the structure is. That is very easy. In the fingerprint region, because it's a complicated vibration, you will always have a difficulty to know what exactly is the different combinations. So what people do is, first they find out what are the functional groups. Now, once you know what are the different combinations possible, you can actually guess. If suppose I have a benzene ring, then I know that there should be 1000 centimeter inverse peak around there. So then I will go and look at the fingerprint region and then look at it. So these are the different ways to counter verify whether it is aromatic, it is not aromatic, various other things. So first you use the the functional groups, then you come to the fingerprint region. But when you are talking about solids, any solid, you will never have peaks above 1500. This 1500 is only for organic molecules, not for your normal solids. Like if you are doing YbCO or you are doing any of this like gallium nitride, you will not have any peaks above 1500. You will not have anything. So there we are not talking about any fingerprint region. There nowadays we have computer programs which you can actually put in the computer program and find out what are the vibration modes present, and easily you can find out whether it is IR mode or Raman mode. And then you can actually analyze the complete spectrum.
So another question, two participants, Dr. Pragya and Manjusha is asking, could you please explain the crystallinity and amorphous?
So this is very interesting question, because there are many reasons why a peak would actually also broaden. The peak broadening is not always related to amorphous and crystalline. See, what happens is that when I told you in a simple harmonic oscillator, the omega is equal to root k by reduced mass. Now, omega is supposed to have single value, and it should be a delta peak. It should not have any spread, because any molecule is vibrating, because the spring constant is unique and your reduced mass is unique, your omega should be one value. But it is not true for a quantum system, because whenever you have a temperature variation, the frequency is having a spread. So when you have a frequency spread, that means k is actually not k plus delta k. So the omega will be having omega plus or minus delta omega. So that means you will have a shape, Gaussian shape. This is basically what you see, a Gaussian spread in your spectra. Now, what happens if you have an amorphous system? In an amorphous system, you have a short range order, but not long range order. So that means your k, delta k is too large. It is too spread. So that means your all amorphous peaks will be very broad. So if I take glass, instead of SiO2 sand, I take SiO2 crystals, I take glass, that is basically your what you have on your window, then the SiO2 there is not having same bond distances. So what happens is that your K plus delta K is large. So omega plus delta omega will be large. So your spread will be large. So you will have a broad peak. So always for an amorphous, you will have a broad peak compared to a crystalline system. Crystalline system, all the bonds are equal or more or less very close to each other. So that means it will be uniform. So delta K spread will be smaller. So that's what I said by spread. But be careful. In some samples, what happens is if you have a electronic interaction, that means electron-phonon coupling. If you have spin-phonon coupling, the width of the peak also goes more. So this width actually is affected by coupling between electronic states and vibrational states, or magnetic states and the vibration states, because there is a strong coupling happening, and that also increases the width. So even though your crystal is crystalline, you may have broader peaks. This is something you have to be very careful, but that you can find out by the properties they exhibit. And then you can predict whether it is amorphous or is it because of the electron-phonon coupling or also because of spin-phonon coupling.
Another question.
Yeah.
Thomas Baby, is Raman is useful for polymer composite characterization?
Yes, definitely. It is useful for polymer composition, this thing, because it actually has, even if it is a polymer is basically supposed to be glassy system. It is more glacier system. So you may have broader peaks, but still there are characteristic peaks associated with the molecule itself. And those characteristic peaks will be present in your spectra. And this will easily help you to find out whether it is a polyvinyl or polystyrene or various other kinds of material. So because everything will look transparent plastic. But if you do a Raman, within seconds you can tell whether it is nylon, whether it is polystyrene, whether it is some polyester. Any of these things you can immediately know, because the spectra is different for each of these polymers. And that means it is easy to identify without even doing any chemical analysis. You can actually find out what the material is.
Thank you, sir. Another question from Subin Kumar. What about Raman spectra of metal complexes?
Metal complexes. So that means what you're talking about, say iron, cobalt or something like that. See, one of the very important thing you should realize, I was talking about group theory and I told you about mutually exclusive principle. So in metallic systems, one of the problems is that you have to see how many atoms are there in a cubic system, right? So if it is an FCC lattice or you have a BCC lattice or cubic systems, what happens is that you will only have acoustic modes, not you will have an IR mode, but not Raman mode. Because if you have an FCC crystal, you have a centrosymmetry. If you have a centrosymmetry, what happens is that you will have either IR or Raman. So this is the reason why you actually see that in the case of a KBR, KBR doesn't have any Raman. KBR has Raman mode, but doesn't have an IR mode. That's why it is used for IR as a material for doing pellets of any system. KBR doesn't. So this is what happens. Now, in a metallic system, most of the metallic systems are cubic in nature. And most of the metallic systems are cubic. Hence, you will always have no Raman, but you will have IR from them. So you will always do IR for these, not do Raman. So that is the reason why metal crystals, you do not have many Raman spectra seen in metal complexes. But if you are an organic chemist and you are talking about metallo-organic systems, then there are Raman modes, because there it is an atom, not a crystal. So that is something which I want those who are chemistry background should understand, that metal-organic materials will have Raman spectra, but metal as a solid will not have Raman because of the cubic nature of their structure, which makes it more IR active, not Raman active. And that also, if suppose the number of atoms per unit cell is more than 1. If it is less than 1, it is equal to 1, then it will not have any Raman modes or IR modes. It will not have.
And Neha Mishra. Sir, can you explain Fermi resonance in relation with IR with any example?
Fermi resonance, okay. So basically what you're talking about, very interesting. What people are talking about is, suppose you have you have always look, even go to the Google and also see, there is something called coupled oscillation. So if I have a pendulum, and same looking pendulum, I have 2 of them, and if I actually connect it with a thread on top of it, this experiment you can do it anytime. You can connect a ball with a string and connect it to another string, and you put the 2 pendulum. Now once you put the 2 pendulum and oscillate one pendulum, when you oscillate one pendulum, suddenly you start seeing the second one oscillates, and after some times you will see they oscillate in opposite direction, and after some time they oscillate in the same direction, and then again they will do this same thing. Now why is this happening? Because there is something called resonance. Because any pendulum has one frequency. That frequency is related to the length of the pendulum, to the gravitational force and other things which you have studied in your +2 level. And if you have the same length of the pendulum and the mass attached to it, you will always have the same frequency. So you have 2 ones which are having exactly the same frequency. So now what happens is that they can have, if these 2 are coupled together, they will have 2 modes. One is this mode, another one is this mode. And this is called the Fermi resonance. So this is Fermi resonance. Now coming to a molecule, if you have C double bond O, C double bond O attached to it, an anhydrous compound. If you have 2 double bond O, this C double bond O frequency is same as this C double bond O. Same thing like what is in carbon dioxide. Carbon dioxide has C double bond O, C double bond O. Both the frequencies are same. So in that sense, you will have a Fermi resonance. So you will have 2 modes. One is at 1378, another one is at 1278. This is called Fermi resonance. Same way, N double bond O, N double bond O. You will have the same frequency that will produce, instead of one frequency, it will produce 2 frequency. One is the symmetric, both going in the same direction, another one going in opposite direction. So this is what is the Fermi resonance, which people talk about in IR, and Raman also.
And the question from Shimon, sir, can we distinguish metal doping from its simple diffusion or composite formation with an inorganic host lattice?
Metal diffusion. Metal means metal ion diffusion, I think. That is what is being asked, I guess. So basically, whenever you have a complex, and if it is a simple diffusion, it will create a stress. It will create a stress, not change the vibrational, the vibrational modes will remain the same, but their frequency will be shifted. So diffusion can be easily found out because they are not getting into the system. But if suppose there is a bond formed between the metal ion and the system, then immediately new vibrational modes will come. And these new vibrational modes will tell you that it is forming a complex, not a diffusion. So this is how you can find out. If it's a simple diffusion, you will find the peaks are actually shifting, not actually changing. So this is how you find out whether it is a diffusion or is it a complexation.
Hello, Bessie, Professor Bessie. I think we can wind the session. We can ask the participants to email Professor Chandrabas questions if they have any, due to lack of time, because we have to move ahead to the next session.
Yes.
So can we wind up? Yeah, can we wind up this session, Professor Bessie?
Yes, miss. Yes, miss.
Thank you. Thank you so much. Yeah.
Okay, sir. It's time to propose vote of thanks. On behalf of the Department of Chemistry, Bishamur College, I extend very hearty thanks to Chandrabas Narayana, sir. We get an excellent coverage on symmetry operations, finding the point group, and a good class on vibrational spectroscopy and its applications. We are grateful for the time and effort you took to share your knowledge with us, sir. Thank you again.
Thank you. Thank you so much. Yeah. Thank you. So I'll log out now. Okay.
Yes, sir.
Thank you.
Thank you.
Thank you, sir. Thank you, sir. Dear participants, we'll take a 10 minutes break and we'll come back at 11:50 because the first session was extended a bit. So we'll join back at 11:50. The feedback forms are here. Make sure to fill them, the feedback forms. The quizzes will be posted, will be sent to you via email. There are two quizzes today. So one quiz from the first session and another quiz from the second session, they will be sent to you via email. And there are 3 assignments and 1 project. All the assignments and the project will be sent to you, communicated to you via email. The deadline for the assignments and project will be 14th October. So you have the weekend and you have time so that you can fill it, you can do the assignments and submit it. We'll be giving you the link for submission also in the email. And the two quizzes, they have to be submitted by 8 p.m. today. So, so first session is concluded. Kindly remain. You can continue to be on this platform. The platform will be active. Kindly remain on the platform, and we'll join back. We'll come back at 11:50. Okay. Thank you. Thank you very much. Good morning, Dr. Srikanth.
Good morning, Princy.
Miss,
Am I audible?
yeah, you are audible. You're audible.
Okay, just tell me where to share this present now.
Yeah, just there's a present now button on the bar below.
Okay. Present.
The present now, it's on the bar below the screen.
Yes, I saw. There are three options. There is entire screen, window, Chrome tab, which will be better because we have been doing it here in MS Teams. So and WebEx. So much.
Okay.
First time in Google.
You can share the app screen, app, and then select the PowerPoint.
Princy,
Yes.
he can press the A window button so that we can.
Or the window button also.
Okay,
or the entire
okay.
screen. Yeah.
First of all, you open the presentation.
Okay. Yes. Now is it visible?
Yeah. It's coming. It's coming. Yeah. Yeah, we can see your presentation now.
Okay. Is it full screen or?
It's not full screen. Can you make it full screen?
Just a sec. Now? Now?
It's coming. It's full screen now. Yeah.
Okay.
Yeah. Professor Shilpa, are you there? Okay. So, welcome back again, dear participants, to the second session of day 2 of the one week online FDP program on instrumental methods of analysis. I kindly invite Professor Shilpa, Assistant Professor, Department of Chemistry, Bishop Moore College, Mavelikara, to chair this session.
Thank you, Principal. Good afternoon to all of you. It gives me immense joy to welcome you all to the second session of one-week faculty development program on instrumental methods of analysis organized by Department of Chemistry, Bishop Moore College, Mavelikara, in association with Guru Angad Dev Teaching Learning Center of MHRD at the FDP Khalsa College, University of Delhi, and St. John's College, Agra. It is great privilege to introduce and welcome speaker of the session, Dr. A. Srikanth. Dr. A. Srikanth is Associate Professor at NIT Trichy. Dr. Srikanth received his Master's and PhD degree from Cochin University of Science and Technology. He did his postdoctoral research in pulse EPR spectroscopy at ETH Zurich, Switzerland, after which he joined NIT Trichy in 2007. His research interests include coordination chemistry of transition metals and lanthanides, DNA binding and biological studies of complexes, organometallic chemistry of semi-carbosones and corrosion chemistry, TED-DFT studies and molecular docking. He has executed major research projects under DST CSIR and DAE BRNS. He has over 50 publications and has guided 4 PhD students, and currently 8 students are doing PhD under his supervision. His teaching interests are spectroscopy, organometallics, and coordination chemistry. With this brief introduction, I invite Dr. A. Srikanth to deliver his lecture. Over to you, sir.
Thank you, Dr. Shilpa, and thank you, Princy, for the invitation. So I will keep my presentation quite simple because you have already learned some vibrational spectroscopy in the previous lecture. So I will not be going into much equation details or group theory wise applications or definitions. So sort of I'll connect my lecture totally to the application side, how vibrational spectroscopy is applied both in analysis as well as in research. So just a few introduction about IR, just as a recap. So basically IR spectroscopy is not used majorly by chemists as a singular analytical tool. It is a complementary tool to NMR spectroscopy, to be frank with. When we were all students way back a decade ago, there was some importance for UV visible spectroscopy in the structural analysis, but that started fading totally. And almost we are now able to analyze the structure of a molecule, whether it is organic or inorganic, without the help of UV. UV happened to be only additional information, not any substantial information providing. On the other hand, UV visible spectroscopy, along with the dynamic light scattering techniques, etc., has become very prominent in nanotechnology and other analytical sciences fields, environmental chemistry or in biology or in bio-inorganic chemistry, etc. Whereas IR still has some scope in structural analysis, especially IR helps us to understand the functional group. So the moment any student looks for the molecule, two things he has or he or she will look for in the beginning: what is the molecular formula which is intended, and then what are all the functional groups present in the system. So IR mainly deals with functionality of the system, and as a spectroscopic technique, it mainly considers or is concerned with the interaction of infrared radiation with matter. So any spectroscopic techniques except mass spectroscopy is the interaction of electromagnetic radiation with matter, and it is kind of related to Einstein's coefficients, etc. These are all matters connected to the preliminary spectroscopic understanding. So whether theoretically one spectra is allowed or forbidden, it's immaterial. What you see in reality or how much you see in reality is very important. So IR spectrum of a compound generally can provide information about the chemical nature and molecular structure. That is a general definition given by textbooks.
Sorry to interrupt, Dr. Srikanth. Sorry to interrupt. Can you please put it in the slideshow mode, please? In the slideshow.
It is in the slideshow mode. How is it visible now?
The slides are visible, but like the next slide is also showing up. Is it in the slideshow mode?
No, just.
Yeah, it is okay now. Yeah.
No, it's okay.
Yeah.
Okay.
Now it's okay. Thank you.
Okay.
Sorry to interrupt.
Okay, no problem. Otherwise, I will not get to know. I had a problem with my HDMI adapters, so I am having only one screen now. So I cannot.
Okay.
My tablet also not working, and my other two monitors are also not working. So I have to handle with only one monitor now. So.
Okay, sir.
So.
Is it okay to present for you in this mode, or is
no
it?
Problem, no problem. I'll just do one thing. I'll just go to the next slide and see whether it is also working or not. We'll see. Then we'll continue. I'm going to the next slide. Is it okay?
Yeah. We can see the next slide. Yeah.
Okay. Yeah. So now it's fine, huh?
Yeah, it's fine.
Okay.
Thank you.
Okay. So coming back, so most commonly the spectrum is obtained by measuring the absorption of IR radiation through infrared emission. Emission and reflections are also sometimes used. And so as a matter of fact, a molecular spectra in total is consistent of several energetic interactions. So what we generally do in the beginning of molecular spectroscopy, we make an assumption that translational motion of a molecule is ignorable, because the kinetic energy of the molecule is ignorable when compared to the potential energy which is inherited by the molecule. So the kinetic motion is approximated that it does not provide any sufficient energetic changes or any sufficient energetic interactions in spectroscopic realm. Later, when it comes to, you have already seen the Raman spectroscopy, where you see that there are effects like for scattering, which is very important in the kinetic energy interactions. That means the molecular motions also play some role in the absorption spectroscopy, but that is only applicable when it comes to the line intensity or line width of the systems. Other than that, it does not play much of an effect on the position of the absorption of a particular electromagnetic radiation. And what we are interested in spectroscopy majorly is where does it get absorbed, or what is the frequency, or what is the wave number, or what is the wavelength at which a molecule absorbs a particular radiation and undergoes a transition. And again, as a chemist, we are not bothered much about what sort of a transition that is going to be, but what is our botheration is what structural information we can gather from that transition. That is the most important part. So larger part of the potential energy of a molecule is spent for the electronic transitions. That electronic transition levels are larger. Then the smaller on each of the electronic energy levels, several vibrational energy levels are built, and each of the vibrational energy levels, rotational energy levels are built. So when you look from the perspective of rotational spectra, transitions between the rotational energy levels are only observed. When you are looking at the vibrational energies level spectra, you are looking on the vibrational energy levels, but at the same time, rotational energy levels also get involved into the vibrational spectra because of the unharmonicity of the system. So that what we in reality observe as a vibrational or IR spectra is a vibrational rotational spectrum. When it comes to electronic energy levels, it is having all the three contributions, but fortunately or unfortunately, we lose all these information in an electronic spectra. Or I think almost every one of you have seen an electronic spectra. It is very broad, and it has a huge line width, and all the transitions we see for example, whatever we are seeing here, is my pointer visible? Princey, is my pointer visible?
Yes, sir.
Okay.
Yes, it is.
So whatever we are seeing here, this larger this is only given with two energy levels. Vibronic energy levels are there, and on the top of it we have rotational energy levels. And as we know from our basic molecular spectroscopy understanding, that rotational energy levels are not equally spaced. Their spacing is not equal, whereas vibrational energy levels absolutely are equally phased, and then J coupling is involved in it. That is why it starts 0 is here, minus ones are and plus one. This should be 2, not 1. So like that, there are transitions possible. So every vibrational transitions are involved with a lot of energy levels involved, and on a simpler aspect, it follows Heisenberg's principle. So when it follows the Heisenberg's principle, the position and momentum, that is position and energy in terms, or position and absorption frequency or wavelength cannot be determined at the same time. So what happens generally is that any unharmonicity in the system, these positions can have aberrations. So what happens is, when the energy levels can occupy, even though they are discrete and quantized, they can occupy variable places, and due to this you will build up with a instead of a stick spectrum, you will end up in a band spectrum. And this uncertainty is larger for electronic spectra. That is why in electronic spectra we generally have huge wavelengths. So in vibrational spectra, what we are interested is only on the vibration of molecule, which is on the basic understanding. We connect it with the Hooke's law for simple harmonic oscillation, and I'm not focusing much over here because this is something which you I'm sure everyone is learned very well. So any vibration of it on a simple terms, M1 and M2 being two molecules, two atoms connected at the interatomic distance r, and with a reduced mass m, will finally give rise to a frequency equation. Oscillator frequency is equal to 1 by 2 pi into square root of f by mu, where f is the force constant calculated from the bond length and bond strength of the system, and mu is the decrease in the atomic mass, or which is called as a reduced mass after the vibrational process is being calculated. So there are several parameters which includes there. This is not a simply derived equation. Those who have gone through Banwell or through any other molecular spectroscopy textbooks will understand that this comes from a larger treatment of unharmonicity in the system, and then also accounting for several values of unharmonic constants, and then taking into account dissociation energy of the system. All these things are included, and this calculation is arrived at. And at the same time, everyone also will know with one thing for sure: after the calculation of this, when you go for the frequency equation, when everything is put down to 0, you still have an energy of the system which is equal to 1 by 2 omega. That is, half of the oscillator frequency still exists even at absolute 0. That means vibration is the only motion in the universe which does not cease to exist even if everything else is dead. So even if rotation is frozen, even if kinetic energy is frozen, electronic energy levels are frozen, no movement takes place, no energy transition takes place. The molecule exists with an energy which is vibrational energy, and that is called 0 point energy in the system. So it is having a huge significance. In that sense, high vibrational spectroscopy has a huge significance, as it is one of the origin of the energies in the molecule. That means the molecule never rests, or any substance or anything which is constructed with a particle that never rests even at a absolute zero. That means it keeps vibrating even at absolute zero. So the treatment is with an harmonic oscillator model. So actual potential energy of vibration fits into a parabolic function. If it is a harmonic oscillator, it's a perfect parabola. Since we are treating with anharmonic model, this perfect parabola is lost. So it has to be like this, and here we have as dissociation energy of the system, and in between we have different vibration energy levels noted as E0, E1, E2, etc. So what generally is done is this E0 is you see that E0 is not at the origin or not at the axis. There is at the, and it is in fact at a small energy, and any oscillator which is moving as a harmonic oscillator, considering the fact that there are no rotational involvement over there, will keep moving with a particular potential, which we call it as Morse potential, and this curve is also called as Morse potential curve in theoretical aspect. So when this energy difference is considered, each of the transition from n to n plus 1 correspond to the energy of the absorbed light in quantum. So delta E is equal to h nu, applicable for almost all the absorption spectroscopy, whether it is microwave, whether it is IR, Raman, electronic. Delta E is equal to h nu is applicable everywhere. This delta E is considered as between the different vibrational energy levels, and then all what you have to think is whether the transition is going to be allowed or forbidden. That's all. So there are possibilities in vibrational spectroscopy. 0 to 1 is generally considered as allowed transition, and then 0 to 2, 0 to 3, etc. are also possible in the case of vibrational spectroscopy. These are called as overtones, and they correspond to delta nu changes 2 or 3, and these frequencies are lesser in 2 to 3 times. That means this is due to the unharmonicity in the system, and the energy of the energy spacings are in such a way that due to the temperature, we have a larger population in the 0th energy levels normally, and as and when you increase the temperature of the system, most of the higher energy levels are populated, and it need not be that you always get a vibrational spectra starting from 0 to 1 transition. It is also possible that 1 to 2 transition, 2 to 3 transition, etc. are also possible when you are when you are going to measure the experiment the spectra at a higher temperature. But nevertheless, delta nu is equal to 1 transition remains. It only means that from what energy level to what energy level it is going. Delta nu is equal to plus or minus 1 transition with a single harmonic transition. That means it is a primary or fundamental oscillator frequency or fundamental vibrational frequency never changes for the molecule, and it only temperature is a factor which decides which energy level is getting populated, and generally it is obeying the Boltzmann population. So one more theoretical aspect is the inclusion of the rotational vibrational transition in it. I'm not going to touch this part at all because Dr. Princy already told to make mostly on the application side of it. But to touch this part, rotational vibrational transitions are generally of interest to people who work on smaller molecules. That means diatomic molecules, triatomic molecules, mostly on the physical aspect of how these transitions work and what is the implication on the physics side of it, etc. We generally, as an organic chemist or inorganic chemist, we do not find much interest in this. Vibrational spectra, when rotational energy transitions are also included, we get into a mixing of rotational energy levels into vibrational energy levels. So as a result of which, each of the vibrational energy levels will be having a lot of rotational energy levels. So as you can see it over here in this next slide, we get to have a fundamental frequency in the middle. Sometimes the fundamental frequency is not at all observed, which we call it as Q branch, and sometimes it is observed. There are cases where fundamental is observed, not observed, and whether they are observed or not observed, like you see in this figure, the fundamental branch should come in the middle, and the branching is due to the rotational energy levels and the rotational energy level transitions occurring. This finer splittings are due to the rotational energy level transitions. This is a high resolution spectrum for HCl, standard textbook format, but this is obtained in gas phase. You will not get this spectrum in solution. You cannot get this spectrum in solid state. You have to get HCl molecule in a very dilute format in a gas phase to have this spectra, so that enough rotational freedom is given to HCl and there are no other parameters binding this. That means the molecule is free to rotate in space. There is no other molecule coming and colliding the molecules, because when collision occurs, the total surface will get either compressed or they get elongated. See, the same thing happens in Raman also. Overall profile of it either get compressed or get elongated, so that the polarizability ellipsoid changes. That makes a change in the energy levels also. So that is one of the reasons you can see that still collision is unavoided. Well, that is why there is a term also in spectroscopy called as collision broadening due of line width. So that is one of the reasons you see that branching is not symmetrical. You see that more distribution in the P branch, less distribution in the Q branch, even though everything occurs at the same place, same sort of intensity profile, but it is not exactly symmetrical in nature. So we have, over a period of time, probably over last 100 years, we have completely utilized the electromagnetic spectrum for the benefit of human beings, starting from gamma ray spectroscopy, where nuclear excitation takes place. Majorly, Mossbauer spectrometers are functioning on gamma rays. There are other techniques also which works on gamma ray radiations, and then X-rays. Generally for X-ray crystal structure and X-ray spectroscopy called as X-ray photoelectron spectroscopy, and UV visible spectra for the UV transitions, and there is a photoelectron spectroscopy also in high energy based on UV visible spectroscopy, and then molecular vibrational spectra, which is called as IR spectra, which in somewhere is sort these two clubs and coming under the visible approximate visible region, and then comes microwave spectroscopy and radio waves. So here it is going to one aspect, this is nuclear. From there it is going to electronic, and all these things are electronic in nature, technically speaking. When you speak about an interaction of electromagnetic radiation with nuclear energy, electronic energy levels, there are two kind of interactions possible. The electrical part of the electromagnetic spectrum can interact with the polarization of the molecule, or the magnetic part of the radiation can interact with the molecule's magnetism. So in IR spectroscopy, what is concerned is the electrical component of the electromagnetic radiation interacting with the electrical component of the molecule. So if there is no electrical component in molecule, there is no spectra. Even if the absorption takes place irreversibly, even if there is a possibility of absorption, there are vibrational energy levels in all molecules. But if the electronic component is not there, it doesn't work. But that is why we have this principle of mutual exclusion when it is compared to Raman spectroscopy. Raman does not look for an inherent electrical component in the molecule. Raman is creating it. That how Raman is creating it, it is creating due to the polarizability ellipsoid. So what is the electrical component in the molecule? To be simple, on simple terms, is a built-in dipole. If a built-in dipole moment is not there in the molecule, you will not see a IR spectra. That is one disadvantage of IR, where it is complemented by Raman, because even if there is no built-in dipole moment in the molecule, we can easily compensate with the spectroscopic technique. When it comes to radio waves, it is the magnetic component which deals with the spectroscopic technique. So it is generally magnetic resonance imaging, magnetic resonance spectroscopy, EPR spectroscopy, quadrupolar resonance, etc., coming in this region. So there are two approaches for IR spectroscopy. As I have told you or shown you in the beginning, there is vibrational rotational spectra, which is mostly physics part of it. And there are people who takes up character tables and analyze it as a proper group theory aspect, whether this vibration is predictable, whether this vibration occurs or not, or whether this transition is allowed or forbidden. That aspect I'm not at all touching. We are directly going into how many type of vibrations possible and how we can find out functional group or what are all the functional group analysis possible in IR spectroscopy. That is the part of my main lecture. So the degrees of freedom in a molecule is generally assumed that there are few type of degree freedom existing in the molecule. So when it comes, or when the theory is built from diatomic molecule to polyatomic molecules, the number of degrees of freedom in general in a molecule, it is assumed that there are 3 degrees of translational freedom existing in the molecule. And then there are possibilities, if it is a linear molecule, then there are 2 degrees of freedom for linear motion and 3 degrees of freedom in the non-linear molecules. So totally, when you can take away these freedom from the molecule, n number of atom, if it is present in the molecule, so total freedom is 3n. So in a vibrational freedom of a molecule is 3n minus 5 for linear molecules and 3n minus 6 for non-linear type of molecules. Only making differences are the rotational freedom. So in the case of linear molecules, or in the case of linear molecules, what happens is the rotational degree rotational freedom is 2 type. One is on its own axis, one is rotation in this axis, and the other one is rotation in this axis. So what is considered in this axis in 2-dimensional molecules, it is considered as producing no dipolar moment in the system as far as linear molecule is concerned. But even in the non-linear molecule, that is not the case. There is IA not equal to IB, not equal to IC. So the moment of inertia are non-equivalent in non-linear molecules, and there 2 of the moment of inertia are equivalent in linear molecules, and 1 of the moment of inertia is different in the case of linear molecules. So 2 degrees of freedom in linear molecule and 3 degrees of freedom in non-linear molecules are taken away from the molecules. So totally in a multimolecular system or polyatomic system, vibrational freedom is 3n minus 5, and in a non-linear molecule, vibrational freedom is 3n minus 6. So this has some implication, because this 3n degrees of freedom, the movement of the entire molecule while position of the atom is related to each other is fixed, and the remaining are provided for the vibrations. So what happens in total is, when you calculate, if it is a triatomic molecule, n is equal to 3. So if you calculate, you will get a number, and this number is how many number of fundamental vibrations can occur in the molecule. Theoretically, you can calculate. There, you don't have to worry about the dipole moment. So this 3n minus 5 and 3n minus 6 is a total calculation immaterial of the dipole moment factor. That means it does not consider the dipole moment of a system. So in total, 3n minus 5 or 3n minus 6, you calculate and you get a number. It is a total number of IR plus Raman vibrations possible. It is not IR alone, it is not Raman alone. Some IR vibrations are Raman allowed, and some are some forbidden IR vibrations are Raman allowed. So what you cannot see in IR, you can go in Raman and look and trace it back. So based on this, we generally have several motions. We assume that certain motions or certain vibrational motions in polyatomic system can provide a dipole moment change. For example, is in the case of a nonlinear system, a symmetric stretch can provide a dipole moment change, whereas in the case of a linear molecule, a symmetric stretch, the same symmetric stretch, if this hydrogen and hydrogen are linear, that means they are directly opposite to each other, then the dipole moment cancels off and the same symmetric stretch becomes IR inactive, and that then becomes Raman active. Asymmetric stretch already in whatever format is IR active, because it is a dipole moment changing motion. And apart from that, there are other motions also. Then when you can see this as a movement properly, so a symmetric stretch is at the same time, so they compress and go away from the system. In a symmetric stretch, they, on the other hand, one is compressing, the other one is moving away. When this is coming back, then this goes away. These are happening, these are in plane motions, or these are generally called as fundamental vibrations, because they happens primarily in the molecule. When you exactly call vibration, this is what vibration means. Rest all are out of plane movement. So I have shown you 6 figures. In this, the only in plane motion is this. All the other 4 are going to be out of plane movement. So like bending is kind of like bending can be in the plane like this, or in this plane also like that. So it can be out of plane. Rocking is same way, this happens like that. And wagging is certainly out of plane with the added torsional angle to the system. That means torsional angle is added as far as the wagging and twisting motions are concerned. But nevertheless, whenever we try to interpret a stretching frequency, it is generally means it is a symmetric or an asymmetric stretch. And most probably there are other cases also occur in organic analysis. Sometimes their bending motions or bending frequencies become very important. So in an approximate analysis, the region in which IR spectra occurs is, as everyone is little bit familiar, we have a general lookout for a middle IR spectrum from 650 or 500 even. Starting from 500 to 4000 is the IR spectroscopic region. Our frequency domain is centimeter raised to -1, even if though it is not frequency, it is wave number. Nobody represents or nobody calls it as wave number. Generally, by default, it comes to mind that it should be frequency. So it is for the sake of fullness of the numbers and sake of representation, frequency is chosen, because otherwise what happens is in wavelength or wave in frequency, what happens is they become pointed numbers. You see here. So to remember, it is very difficult to tell that, for example, carbonyl stretching frequency at 6.2 lambda. So that looks very odd for us. We'd never remember that. Instead of that, somebody says 6,670 centimeter raised to minus 1. It's easy for us. So this is the only reason people stuck to this type of notation, even though it is a very old notation. So you see that there are general organic functional groups all fall in this region, but doesn't mean that there is no IR spectroscopy beyond this region, and there is no IR spectroscopy beyond this region. Beyond this region is called near IR, this is called middle IR, and beyond this region it is called far IR. And there is a huge techniques available on both sides. Near IR spectroscopy is almost like, because that is a tailing end of UV spectroscopy. Near IR spectroscopy has a lot of defense applications, and also applications you can find in space technology, because that is where things become stealth, in the stealth mode. So a material which absorbs in near IR region, many of them the normal scanning machines cannot find, or they cannot observe that. So it is kind of a stealth appearances. Lot of huge luminescent applications exist in the near IR region. On the other hand, for inorganic chemistry, material chemistry people, this region becomes very important, because the metal oxygen, metal nitrogen, metal sulfur, or metal chlorine, these type of vibrations, they are dominant in the region beyond 650. So 30 to 650 is the region where we generally have a huge spectral interest. But mostly whenever we say IR spectrometry, this is this region. So what happens is, in IR spectra, we have our primary interests are on looking at different alkyl groups, or anhydrides, or amines, or nitro groups, or whatever groups possible. We generally account in this way. So you see that, for example, for a symmetric stretch of an alkyl group and an asymmetric stretch of alkyl group, there are different possible fundamental frequencies available. And depending on where this methyl group is going to be attached, this value also changes because of the electronegativity changes in the molecule, and because of the overall dipole moment change in the molecule. There can be an increase or decrease in these values. So these values are approximated values, always plus or minus 30 to 40 centimeter raised to minus 1 changes can occur from molecule to molecule. And second part is anhydride, another important functionality. There is a very clear indication if an anhydride exists. You have two carbonyl vibrations, one due to the asymmetric stretch, and other one due to the symmetric stretch of the molecule. So like that, there are possibilities. Sample IR spectra, I think everyone might have seen an IR spectra. It looks more or less like this. The x-axis is represented with transmittance, and y-axis is x-axis is represented with wave numbers, and y-axis is represented under percentage of transmittance. That is very important thing in IR, because by tradition it is represented in percentage transmittance. In UV visible spectroscopy or in absorption spectroscopy, we generally represent the y-axis in percentage of absorbance. This is only due to the technical differences in the instrumentation part, because in UV we generally use a photomultiplier tube for the detection. In IR we do not use a photomultiplier tube. What we have is a kind of bolometer or gradational thermocouples for the detection. So only due to the sake of detection limitations, we stick on to the transmittance mode of the spectra. So generally, there are some interesting parameters which we look in IR. So whenever IR spectra comes to mind, we have to look for the functionality in the molecule. Some functionalities incidentally occur at the same place. So you have to have an idea whether to call a functional group a proper functional group. So for example, you have a molecule with a carbon, hydrogen, oxygen and nitrogen in the molecular formula, then we have to cleverly identify whether the carbon oxygen bonding is a carbonyl or a OH, or a carbon nitrogen bonding is a primary amine or a secondary amine or a tertiary amine, or none of the above, it is an amide, or it can be a C double bond N as in azomethane linkages or the shift based linkages, etc. This we have to cleverly assess. The main problem being this region 3200 600, this region almost all the time amine and OH comes in the same place. If you have both amine group and alcohol group in the same place, it is rather very difficult to distinguish. But one good thing is that mostly OH will appear very broad, because this hydrogen is very active, it keeps coming and going from the system, so OH is very active, and compared to that amino group vibrations are quite sharper. So this leads to one good thing in IR spectroscopy. We can this is quite applicable in biological systems where hydrogen bonding is very prominent. So biological activity of DNA or RNA binding or unbinding. So in our research and all, what we do generally is to use our molecule which we have synthesized, to mix it with a protein or a DNA and see that there is a binding or a cleavage in the system happens or not. And whenever it cleaves, there is a binding in the system and is unwrapped. So certain targeted systems can be focused directly by IR spectroscopy. So from a broad band that goes to a sharp band, or a sharp band goes to a broad band due to the changes in the hydrogen bonding of the system. So essentially speaking, there are two types of bonding interaction taking place in a molecule. Everyone knows intramolecular hydrogen bonding and intermolecular hydrogen bonding. So what happens is intramolecular hydrogen bonding illustrated within the molecule, and intermolecular hydrogen bondings are between the molecule. Intermolecular hydrogen bonding decreases with dilution. Intramolecular hydrogen bonding never changes with the dilution. So what happens is you dilute and keep taking the same type of IR spectra. If a profile of the one particular peak does change, then that is corresponding to intramolecular hydrogen bonding. And if the profile doesn't change due to time, then it is corresponding to the intermolecular hydrogen bonding. So if, for example, this here we can see is what we can see here is different type of hydrogen bonding existing in the system. So the same molecule here is hydrogen bonded OH, is very large. This actually it may look very simple to you, but on I think for the people who have really taken IR spectra and observed, if you mess up with your sample, you will get this peak. That means if there is a huge moisture content in the sample, or if your sample is not purified properly, it is affected by external water, then again you will find such peaks in the spectrum. So always this region is very dangerous, very carefully manipulated, very carefully understood. And along with that, if aromatic or aliphatic vibrations exist, that also contributes over here. So this region, this 2800 to 3500 600 region, has to be handled in a very delicate fashion, where you see free OH, hydrogen bonded OH, and if only free OH exists, how these changes are there. But at the same time, if somebody pours some water in your sample, you have the same situation, or you will have the same type of spectra. When you see that percentage of transmittance is nearly 100% over here, whereas a free OH is not a strong stretching frequency. It is a weak stretching frequency in compared to a stronger frequency like that. So we'll see in a minute what is the difference between a stronger frequency, weaker frequency, and a medium frequency. But however, you see that a small mistake can completely end up frustrating your system. So hydrogen bonding is a very important effect which can be observed in IR spectroscopy, and it influences the stiffness in the molecule, and it influences the alters the frequency of vibration, and it also provides a lot of information about solvating effects, etc. In the system. So following slides are like some examples of how a classification occurs, or how general vibrations are there. So anyway, I'm going to share this slide with Dr. Princy so that she can share it as course materials to everyone. So probably we don't have to worry much on individual part of these slides. So this is some data corresponding to where the or kind of a correlation chart where these transitions can occur. So it almost happens to have all the bonding systems. CH, how many different type of CH exist? For alkanes, bend, stretch, alkenes, stretch out of plane, aromatic stretching, alkynes in the case of aldehydes, how many different types. So you start from one end, you start to another, end up into 2700. A huge region is allocated for CH. C single bond C alkane stretch. This interpretatively not a useful technique, because when you take a organic molecule, so many C single bond C exist. So generally speaking, nobody is interested in an alkane carbon-carbon single bond, whereas carbon-carbon double bond is very important. Sometimes a medium to weak, very specific peak can be seen over there. Triple bond C is very important, because there are very few techniques where we can identify a C triple bond C, a C triple bond N, that is a nitrile stretching frequency. Very few techniques we can. For example, you have a molecule, you have a carbon and nitrogen. Unless otherwise you do not have a proper IR spectra, it's very hard to judge the structure of the molecule if it is a nitrile, because NMR can give rise to few possibilities where all of them may be correct sometimes. So especially when those who engage the students with combined spectroscopic problems, what we generally do at that time is we give them molecular formula and then ask them to arrive at minimum structures possible, and then try to fit in the IR spectra over there, and then try to fit the NMR spectra in there. That is how they arrive at one particular structure, and they can simply say this is the structure of the molecule for final. So when you do that, IR plays a huge role, very important role as far as C triple bond C and C triple bond N is concerned. Apart from that, aromatic or aliphatic, aldehyde, ketone, carboxylic acid, ester, amide, and hydrate, acid, chloride stretching frequencies are very important, and we can very clearly see the differences in the system. Apart from that, ether link is another thing which IR focuses on a lot. Is not much of the systems can find out. C single bond O. Same what happens with C single bond N. Here you see that halide is not much of a use, because this comes in a region which we call it as a fingerprint region. So halide, picking up halides are very difficult. But on the other hand, sulfur oxide, sulfoxide, sulfone, sulfonyl chlorides, etc. Then allenes, nitro groups, nitroso groups, nitriles, imines. Very specific stretching frequencies exist in them. So this is that gets quite interesting. So some selection rules understanding has to be there. So what happens in selection rule is we have calculated everything and we have put up a complete system, and we say that okay, energy associated with the quantum of light can be transferred to a molecule that undergoes a transition change, and then dipole moment of this is greater than the electronegativity difference. The atoms in a bond get absorbed, and vibrations which do not change the dipole moment becomes IR active. Vibrations which change the dipole moment become IR active. So dipole selection rules are generally placed based on that, on a simple affair, whether dipole is existing for a particular vibration or not. This generally is applicable to almost all the nonlinear or linear systems, and we sometimes this is one of the reasons for accidental non-occurrence of some transitions. You expect you have a carbonyl, but due to some other effect in the molecule, this carbonyl stretching frequency is masked totally, or it should be a strong frequency, but it sometimes becomes a weaker frequency. So the theoretical number of fundamental vibrations is never observed. On the other side, you have huge number of band also in IR. Sometimes overtone, combination frequencies, difference frequencies, Fermi resonance band also occurs. And on the other hand, there are much other effects which reduces the number of theoretical bands, frequencies which fall outside the spectral region of the middle IR. So if a frequency falls above 4000 or below 400, a middle IR spectrometer cannot see it. For far IR spectrometer, we need separate instrumentation. For NIR spectrometer, we need separate instrumentation. So both require totally different spectrometers. You cannot see it with a normal IR spectrometer. Band which are too much weak, they are too close so that they coalesce. That means when there are some limitations in which two band can come together. As and when they come together beyond a limit and they come under the Heisenberg's principle of this time and positioning, they coalesce and they occur as a single band. This is a major occurrence in IR spectra. In NMR also this exists. To some extent, coalescence frequencies can be avoided by reducing the temperature. As and when you lower the temperature, the coalescence will go away, and distinctly you can see the two different peaks. Occurrence of degenerate band from several absorptions of the same frequency. Incidentally, you have one molecule, two different functional groups. Due to the electronegative effect of two different places, the two different functional groups which look alike can come also in the same place or absorb also in the same place, which is masking each other. So that means you expect a C double bond N, a C double bond O. Due to the speciality in the molecule, they occur at the same place. You are looking either at CN or CO. Both is there in the same line, but you never understand they are existing in the same line. And lack of major changes in the molecular dipole also is one reason. So group frequencies, we can generally call groups frequencies with certain functional structural parameters involved in them. Even though they are called as group frequencies, these are all approximated frequencies. Molecule to molecule, they change. Dipole moment to dipole moment, they change. So it is kind of a range which is always given. For example, carbonyl, we give always a range. We never pinpoint a particular place and say that this is the only place carbonyl should exist. They exist in a range. So how do you go for an IR analysis? Dr. Princey, how much time I have more?
Dr. Srikanth, another 15 minutes? Yeah. Another 15 minutes?
Just remind me once again, because I have more slides.
Okay,
and
okay.
So.
Okay, sir. Our first session lagged a bit, so sorry about
That
that.
is no problem. So generally what happened is like even if for our classes and all, even if I plan with a lesser number of slides, then the slides gets over easily. So I normally plan with more slides. so what
Okay,
happens is in a general IR analysis, we have to keep asking after looking at the spectra. We have to put certain questions first and then try to answer them one by one. That is how the approach generally happens. Rest all comes with experience. That means the more spectra you see, the more easily this question answer session goes into your mind. So our students, whenever they start working on the combined problems, they take for initial one or two problems, they take around 10 to 20 minutes to solve a problem. Finally, they arrive at 2 to 3 minutes or even less than 3 minutes to solve the problem completely. So these questions which we ask in mind has to be very fast. Whether carbonyl is present or not, that is the first question to be asked if you look at the IR spectra. Because carbonyl gives rise to a very strong absorption at this region. This is a peak which you never want to miss, or this is a peak where you never want to misjudge that this is going to be carbonyl. So before that, you should have a fairly good understanding about what it means to be a molecular formula. So I think I'll conclude my lecture with what it means to have a molecular formula. So so carbonyl is one thing which is very primary to recognize in an IR spectra. So if carbonyl is present, what sort of a carbonyl is that is? Whether it is part of an acid, amide, ester, anhydride, aldehyde, or it is a ketone. So when you have to strictly adopt this, because otherwise you will mess up. So acid is there, then counterpart OH should be there. Amide is there, counterpart NH should be there. Less ester is there, then a very strong intensity carbon oxygen single bond stretch should be present. Anhydride always means you should have two carbonyl absorptions. Aldehydes means that aldehydic CH should be present. So they are also distinct and weak. So these regions are quite neat regions. So this 2400, 3400 region, unless otherwise, you normally know that when unless otherwise they are amino acids, this region is undisturbed. If it is an amino acid, then sutranic effects and all other effects also exist in the system. This region is very complicated, I agree. But apart from that, if it is no amino system present in the system, this is quite clean. If amides are there, amino NH stretch you can observe. And if it is ester, this region, even if it falls under kind of fingerprint region, this is a very strong band for ester carbonyl, carbon oxygen single bond. Anhydrides, as we have seen in the previous slide, has two absorptions, one at a higher frequency and other one is a lower frequency. Aldehydic CH also present in this region. This is a quite neat region in IR spectra with a baseline only. So you can pinpoint an aldehydic. When all these are eliminated, yes, ketone is present in the system. If this is absent, then you are looking for other options, whether alcoholic OH is there. If that is the case, whether it is phenolic or aromatic, non-aromatic system, or it is amine or ester or ether. And if the double bond is there, well, what sort of a double bond it is? Whether the carbon-carbon double bond is a weak absorption near 650, whether it is aromatic or non-aromatic, they make a difference, which is vinyl or allylic. They have specific absorptions. As I have told you, this is very important. C triple bond N is a medium, very sharp and medium, and this region almost never goes wrong. This number is something like a magic number, it never changes also. Maybe maximum like 10 centimeters to -1 up and down change occurs in the system, but it's very clear. C111C is a weak spectra, and it is lower in frequency than this. This region is very neat, so we can very easily pinpoint from the triple bond. Nitro groups also has very strong absorption band in this region. This happens to be carbonyl region, so you should be very careful interpreting the system in the presence of a carbonyl. That is one thing which is very, very important. Hydrocarbons, if nothing is there, it's a clear hydrocarbon system. So that is how you go for an analysis. So how does or what differences? So these are all tables which I'm going to share the PPT to Dr. Princy, so you can go through it. So one another aspect is the ring size can be found out technically looking at ring ketones. So cyclopropanone, cyclobutanone, cyclopentanone, cyclohexanone, you can see a very gradation in the frequencies. Looking at that, the ring size can be determined from the system. So analysis box, so you should have kind of an analysis box in reality. Check them. So reality, you should not have it in a pen and paper. This checking should happen in the mind. The more faster you do it, the faster you can assign a functional group to the system. And in the end, there is one thing which we should know how to play with the molecular formula. So that is very important as far as so the applications also runs to inorganic chemistry part. So inorganic chemistry, it's getting more complicated because inorganic chemistry, all these functional groups are applied in inorganic chemistry either as a ligand or as a substitution, isothiocyanate groups, isocyanate groups. Beautiful absorption frequencies, very easily we can pick them up. On the other hand, the structure of the system also can be quite easily recognized. So I want to conclude with one thing which I always talk in my classes also, is how to handle with the molecular formula. So when we handle with the molecular formula, this is something which we learn in our BSc classes, is index of hydrogen deficiency. Most of the people know it as carbon double bond equivalence. We calculate generally this for the purpose of how much double bond is present in the system. But on the term of spectroscopy, or in terms of spectroscopy, this is quite useful in connection with IR and mass spectroscopy. You have to connect them together. That the hydrogen deficiency indicates how many unsaturations are present in the system. But it is not only the count of a carbon-carbon double bond. It also can give you a fair information whether the molecule has ring structures or not. So the equation runs like this: carbon, number of carbon minus hydrogen by 12 minus halogen by 12 plus nitrogen by 12 plus 1. It excludes the sulfur containing, that is that group, oxygen, sulfur. So if you have S double bond O, like in sulfoxides or sulfones in the molecule, that does not count here. That means that double bond is not counted over here. Since a carbon oxygen double bond is connected to a carbon, that will be occurring over here. So when index is calculated, one simple example as I can show before I conclude, index is calculated for this molecule is 5. So you have this is benzamide, and index calculated for this molecule is 5. And when you calculate this molecule, 3 of them is attributed for the 3 double bonds in the aromatic ring. 1 is attributed for the C double bond O, and the remaining 1 is attributed for the ring. So always it so happens that when ring structures exist, depending upon the number of rings, the index also increases with 1 point. So whenever we have index in polyatomic systems, you should also think the possibility of having 3-membered ring, 4-membered ring, 5-membered ring, whatever possibilities occurring in the system. Incidentally, when we do not pay attention to this part, we can end up in elucidating the structure wrongly. So that possibility always exists. So beginning of the analysis itself, take up the molecular formula and arrive at a index value, and then have a carbon skeleton constructed. On that, possibly all the functionalities can be arranged, and then look for the valency matching. That means when you valence, first have a carbon skeleton, fix up certain functional groups which you know, remaining all the places you put hydrogens, you may end up with 1 or 2 or 3 or maybe maximum 4 number structures. Looking at the IR spectra, you can fix up to 1 or 2 structure from the many of them. Then go for an NMR spectra where you can correlate each of them, and finally you can round up one structure. This is my structure of the molecule, and we can conclude like that. So I hope my time is also up. Even though I wanted to cover some instrumentation part, I'm probably stopping over here. Princy.
Thank you, sir.
Thank you.
Thank you for your informative presentation. Participants can post your questions and doubts in the chat box. Okay. Sir, we have a couple of questions.
Yes.
Should I read out?
Yeah.
First question is from Neha Misra.
Okay.
Question is, what is the vibrational mode for nonlinear activated complex?
Nonlinear?
Activated complex.
There are no single modes present for nonlinear molecules. Multiple modes are present. So activated complexes means it is a huge system where both are included. So when you see in that aspect, there is stretching and asymmetric stretching does not play much role. In the case of activated complexes, out of plane bonding or twisting type of motions has to be more considered.
Next question is from Thomas Baby. Question is, can we rely on IR spectra for the characterization of metal sulfide like cadmium sulfide?
Yes, but you need far IR. You certainly need a far IR machine. Because mostly this stretching, I would refer to Nakamoto, where inorganic spectroscopy is the IR spectroscopy is dealt with. When you have part B of Nakamoto, you will see a lot of stretching frequencies corresponding to metal sulfides, and you will have an idea where to look, a startup idea, because textbooks all deal with middle IR. And we do not have any textbook in our studying systems which deals with metal, sulfur, metal, nitrogen, etc. So certainly it's going to be below 400 centimeter raised to -1, or somewhere near to 300, 400 centimeter raised to -1. One has to look into properly with a far IR analysis. A separate spectrometer is required for that.
Okay. Next question is from Subin Kumar K. Explain IR bands of primary, secondary, and tertiary amide. What result obtained when a keto group coordinated with metal after enolization?
Okay, Dr. Princy, I will share the PPT with you. So what he has asked, first part of his question is there in the slide itself. So you can share it, I'll convert it as a PDF and share to the participant. Second one is like when you, after enolization, it is coordinated to a metal complex. What happens is, first of all, the double bond tendency is gone. So the stretching frequency is lowered totally. So complexation is very, very clear. The moment the carbonyl complexes with enolization or without enolization, two things happen. Without enolization, if the carbonyl coordinates, it is lowered by 60 to 70 centimeter raised to -1, and with enolization, it is lowered much higher, 100 to 200 centimeter raised to -1.
Okay. Next question is from Madhav Bandru. In Raman spectroscopy, light is scattered. Then, how the vibrational energy levels change?
No, whether it is scattering or absorption or transmission, this all occurs in the same platform. So it is in the case of Raman, what we are observing is due to the scattered light. So whenever a light falls on a system, that causes the necessary vibrational change. There is no doubt about it. But what we are observing, are we observing so when light falls on this, am I observing from the same side? Am I observing from one side, or am I observing from the other side? That makes only the difference. So it doesn't mean that since it is scattered, absorption doesn't take place. Absorption definitely takes place, but only thing is that what we are seeing or from which direction we are seeing the system is important.
Next question is from Dr. Pragya. Could you give an example of aliphatic ester or amide for H index?
For
H index.
I think that you can share the PPT. It is having.
Next is from M. Sharavana Kumar. How IR is used for quantitative analysis?
IR can be used for quantitative analysis. I did not reach that part of my presentation. Exactly for most of the functionalities, especially strong absorption frequencies and that too stretching frequencies follow explicitly Beer's law. So using Beer-Lambert law, we can very clearly assess the system. So the absorptions which are completely allowed transitions like carbonyl, etc., can be used for quantification using Beer-Lambert law. Same way you perform your UV visible titrations, you can do that with IR.
I think there is no more questions remaining. On behalf of organizing committee, I take this opportunity to thank Dr. A. Srikanth for honoring our invitation in spite of his busy schedule and delivering the talk on vibrational spectroscopy so beautifully and interestingly, starting with the very basis of vibrational spectroscopy for the benefit of all participants who are attending the talk. Thank you very much, sir, for your wonderful and informative presentation. Thank you once again for being with us.
Thank you, Dr. Shilpan. Thank you, Princey. Hope everything
Thank
is
you.
running
Thank you.
fine.
Thank you very much.
Thank you,
Thank
sir.
you. Thank you, Dr. Srikanth, for being so gracious to accept the invitation and give this wonderful talk. He talked on IR spectroscopy in a very simple manner, but at the same time in a very effective way. And also thank you for sharing the slides with us, which will be very helpful for the participants. They have already started asking about the slides. And it also will be helpful for them in future for their teaching career. So thank you. Srikanth has been a very good friend. Actually, we are classmates from MSc in Cochin University. So thank you, Srikanth. Thank you very much for accepting the invitation.
Thank you, Prince. Like probably in 10-15 minutes, I will share my slides to you, so you can share to the.
Okay. Thank you. Thank you very much. Thank you. So for the information for participants, as we said, there will be 3 assignments and 1 project that you have to submit for the FDP. The assignments will and the project will be intimated to you through email in the afternoon, and the quizzes. There will be 2 quizzes today, and the quizzes, the deadline will be 8 p.m. and the quizzes will be sent to you by 2 p.m. To those who have filled the feedback forms. So kindly fill in the feedback forms, which is available in the chat box. So thank you. Have a good afternoon, and we will see you all tomorrow, same time. Our first session for tomorrow starts at 10 a.m. And tomorrow we will be talking about mass spectrometry and the analytical aspects of mass spectrometry will be dealt with Dr. Jobin Suriek from IIST Trivandrum. So see you tomorrow, same platform, same time. Thank you all of you.